In this journey tonight, we step into the quiet space where the smallest fragments of reality meet the vast, reaching curves of the cosmos to understand a bridge that has not yet been built. At the smallest scales of reality, the universe behaves with an extraordinary and rhythmic regularity that serves as the silent heartbeat of everything we see and touch. Particles appear and interact in a delicate dance of existence. Energy shifts between forms with a grace that seems almost choreographed. Light moves, scatters, and settles into patterns that can be predicted with a precision that borders on the uncanny. Even uncertainty, that famous hallmark of the subatomic world, follows its own set of rules, unfolding within carefully measured limits that define the boundaries of the possible. From these tiny, flickering interactions, the entirety of the visible world begins to emerge. Atoms form stable, reliable structures that allow the ground beneath us to feel solid and the air around us to feel light. Chemistry unfolds with a quiet reliability, allowing life to persist and the properties of materials to remain constant. The glow of distant stars and the silent, invisible workings of the modern technology you hold in your hands all trace their lineage back to the same underlying framework. It is a theory so successful, so deeply tested, that it seems to explain almost everything the universe chooses to do within the microscopic realm. And yet, threaded through this immense success, there is a singular, quiet exception that remains one of the most profound puzzles in the history of human thought. Gravity is everywhere, a persistent and gentle presence that shapes the world from the moment we open our eyes to the stars. It is the force that guides the falling rain in a straight, determined line toward the earth. It is the architect of the rolling tides, pulling the vast oceans toward the moon and back again in a cycle that is repeated for billions of years. It governs the slow, majestic motion of planets as they follow their elliptical paths through the cold silence of space. Gravity gathers stars into swirling galaxies and possesses the power to bend the very paths of light itself, warping the geometry of the vacuum into something dynamic and responsive. It acts continuously, smoothly, and without interruption, influencing matter across distances so vast they strain our human intuition. When physicists attempt to describe this universal pull using the same quantum ideas that work so perfectly for every other force of nature, something subtle and fundamental begins to unravel. The calculations, usually so robust and reliable, no longer settle into meaningful or stable answers. Predictions lose their physical grounding, dissolving into mathematical expressions that refuse to cooperate with reality. This is not a small flaw or a minor, unfinished detail that can be smoothed over with more data. It is a deep and profound mismatch between two entirely different ways of describing the nature of reality. One of these descriptions is built on the foundation of probabilities, discrete events, and a grainy, pixelated view of existence where things happen in jumps and steps. The other is built on the idea of smooth structure, continuous geometry, and the elegant warping of space and time. These two frameworks are extraordinarily successful in their own right. Both are supported by decades of rigorous observation and experimental proof, and yet, when they are brought together in the same room, they refuse to fully agree. What remains in the wake of this disagreement is a gap at the heart of modern physics. This is not an empty space or a void of knowledge, but rather a place where our understanding becomes tentative and soft. It is a region where our previous certainties begin to melt away, and where one of the most familiar forces in existence quietly resists our best attempts at explanation. Tonight, we move through that gap, not to force a quick answer or to solve a puzzle that has lasted a century, but to explore why it exists and what it reveals about the mysterious universe we inhabit. Settle in and allow your mind to let the questions stay open. Let the weight of your body be supported by the very gravity we are here to discuss, and allow the universe to unfold slowly as we begin our journey into the architecture of the invisible. Modern physics did not grow from a single unified idea, but rather from two very different lenses looking at the same reality. On one side, we have a framework designed to describe the smallest scales imaginable, a world where matter is not solid or continuous, but is instead broken into tiny, discrete pieces that behave in ways that defy our everyday logic. At this scale, particles do not follow the neat, predictable paths of a thrown ball. They spread out like a mist, they interfere with themselves like ripples on a pond, and they only settle into definite outcomes when they are measured or observed. In this realm, cause and effect still exist, but they are wrapped in the soft blanket of probability rather than the hard edge of certainty. This way of thinking emerged in the early part of the 20th century, born from a time when experiments began to reveal that atoms were not just miniature versions of the objects we see in our daily lives. Electrons did not orbit the nucleus like planets around a sun in a clean circle. Light did not always behave like a smooth, continuous wave traveling through the air. Instead, energy arrived in discrete packets, never in between, suggesting that the universe had a grainy, textured surface beneath its seemingly smooth exterior. Quantum physics was built specifically to navigate this strange and flickering territory. It does not ask where a particle is in the usual sense of the word. Instead, it describes a field of possibilities, a mathematical map of where a particle might be, and how likely each of those possibilities is to occur. The predictions it makes are not vague or poetic, they are astonishingly and frighteningly precise. They are so accurate that the same mathematical ideas now underpin the lasers that transmit our data, the medical scanners that look inside our bodies, and the atomic clocks that keep satellites aligned with the surface of the Earth. Despite its reputation for being weird or counterintuitive, quantum physics is one of the most successful and reliable theories ever constructed by the human mind. Its predictions have been tested repeatedly across countless laboratories and under extreme conditions, and they continue to hold true with quiet confidence. When it is applied to the world of atoms and molecules, it works with a level of certainty that makes it feel complete within its own proper domain. On the other side of this divide sits a very different framework, one built not for the tiny and the flickering, but for the immense and the eternal. Gravity, as we currently understand it, is not treated as a force passing between objects in the traditional sense of a pull or a tug. Instead, it is described as the very shape of space and time themselves. Massive objects like stars and planets do not pull on one another across a void. Instead, they alter the geometry of the space around them, much like a heavy weight placed on a stretched fabric. Other objects then simply follow the paths laid out by that curved geometry, moving along the contours of the universe itself. This picture comes from a theory that speaks a language of smoothness and continuity, where quantum physics deals in jumps, gravity deals in flows, space curves gently, and time flows at different rates depending on how fast you move or how much mass is nearby. On the larger scales of the cosmos, gravity creates a sense of order and structure rather than chaos. It has been tested with equal success, correctly predicting how light bends near the sun and how the universe itself is slowly expanding over time. Both pillars of modern physics are sturdy, reliable, and tested to a degree that is difficult to overstate. The oddity we face is not that these theories exist, but that they do not speak to one another in a way that makes sense. Quantum physics assumes a background stage where the drama of particles unfolds, a stage that is stable and taken for granted. Gravity, however, insists that the stage itself is an active participant in the story, stretching and evolving in response to the actors. Individually, each makes perfect sense. Together, they describe reality using assumptions that do not naturally align. It is like having two maps of the same forest, one showing the microscopic life of the soil and the other charting the movement of the tectonic plates beneath. Both are true, both are accurate, but they do not yet overlap into a single seamless picture. As we drift further into the night, we will look at how these two maps might one day find their common ground and why the mystery of their separation is perhaps the greatest invitation the universe has ever given us. To understand why the union of gravity and quantum mechanics is so elusive, we must first appreciate the staggering success of the world of the small. Quantum physics is often introduced as something strange, counterintuitive, or even unsettling. But before it became associated with uncertainty and paradox, It earned its place by explaining things nothing else could. At its heart, quantum physics exists to describe how nature behaves at very small scales, scales far smaller than dust, cells, or even the most complex molecules. These are scales where matter no longer behaves like solid objects moving through space, but instead reveals a more delicate and intricate structure. Atoms were one of the first clues that something entirely new was needed. Early models of the 20th century imagined atoms as tiny solar systems with electrons circling a nucleus in neat circular paths. But experiments quickly showed that this picture did not match the reality of the universe. Electrons did not behave like miniature planets. They did not occupy just any orbit they pleased, nor did they spiral inward as classical laws suggested they should. Instead, they settled into specific, allowed arrangements with precise energies and predictable patterns. Quantum physics provided an explanation that worked with a quiet, undeniable authority. It showed why atoms are stable, why electrons do not collapse into the center, and why different elements have distinct chemical properties that allow the world to be diverse and colorful. Without this understanding, the periodic table would be little more than a list of isolated observations, a collection of facts without a unifying reason. With quantum physics, chemistry becomes orderly and deeply predictable. From atoms, the theory extends naturally to the fundamental particles themselves. Electrons, protons, and other components of matter are not treated as tiny billiard balls bouncing off one another. They are described through probabilities spread out in space, capable of behaving like waves under the right conditions. This description sounds abstract, and perhaps a bit distant, but it produces results that match experiments with an astonishing accuracy. When physicists calculate how particles should scatter, interact, or decay, quantum predictions line up with what detectors observe to an extraordinary degree. In some cases, the agreement between theory and experiment extends to many decimal places, a level of precision that is not common in most branches of science. It reflects a theory that is not merely approximate or a good guess, but one that is deeply tuned to how nature actually works at its most basic level. This precision is the bedrock of our modern world, even if we rarely stop to notice it while we go about our daily lives. Light is another area where quantum physics quietly and brilliantly excels. Once thought to be a smooth, continuous wave moving through space like ripples on a lake, light was found to behave in ways that waves alone could not explain. It arrived in discrete packets, or quanta. It knocked electrons free from metal only when it carried a specific amount of energy, regardless of how bright the light was. Its color mattered more than its intensity in certain interactions. Quantum physics unified these observations into a single cohesive picture. Light could behave like a wave or like a particle, depending on how it was observed. This was not a failure of logic, but a refinement of it. The theory did not insist on a single rigid metaphor. It instead followed cosmic evidence. This flexible and honest approach proved remarkably powerful. It allowed scientists to predict how light interacts with matter, how it is absorbed and emitted by atoms, and how it can be controlled with exquisite precision. The result is not just a deeper intellectual understanding, but practical technology woven into the very fabric of our daily existence. Lasers, for example, rely entirely on quantum principles. They work because electrons in atoms can be nudged into specific energy states and then coaxed to release light in a controlled, synchronized way. This synchronized light is what allows us to scan barcodes, perform delicate surgeries, and send vast amounts of information across the globe in an instant. Medical imaging devices also depend on the quantum behavior within atomic nuclei to see inside the human body without surgery. Solar panels convert sunlight into electricity using effects that make sense only through quantum descriptions. Even the device quietly keeping time for navigation systems and global communications relies on the world of the small. Atomic clocks measure time by tracking transitions within atoms that occur with extraordinary regularity. Their accuracy is so high that losing or gaining a second would take longer than many human lifetimes. This reliability is not a matter of luck or coincidence. It is a direct consequence of quantum rules being both subtle and exact. What makes all this especially reassuring as we drift into thought tonight is how thoroughly quantum physics has been tested. It has survived challenges across decades, in laboratories around the world, and under conditions ranging from extreme cold to immense energy. Each successful prediction reinforces the confidence that, at least within its domain, the theory is describing something profoundly real. Importantly, quantum physics does not succeed by being vague or mystical. While its language involves probabilities, those probabilities are themselves sharply and mathematically defined. It does not say anything can happen any time. It says exactly how likely each outcome is, and those likelihoods match what experiments reveal when they are repeated millions of times. Central to this predictive power lies a mathematical framework that governs how quantum systems change over time. In its most famous form, this relationship is captured by an equation that describes how the wave description of a system evolves. Written out in simple words, it suggests that the total energy of a quantum system is linked to the rate at which its wave description changes with respect to time. This equation does not tell a story in plain, everyday language, but it works with a consistency that is hard to argue with. It allows physicists to calculate how atoms behave, how particles move through a vacuum, and how systems respond to external influences. Its success is measured not by how intuitive it feels to our human senses, which evolved to deal with large objects, but by how consistently it matches the reality of the universe. Despite its reputation for mystery and spookiness, quantum physics is deeply conservative in practice. It does not allow wild deviations or lawless behavior. It enforces strict rules. Some energy values are permitted, while others are strictly forbidden. Outcomes are constrained by the laws of symmetry and conservation. Nature at small scales turns out to be surprisingly disciplined and orderly. This discipline is why trust in theory runs so deep. When quantum physics is applied correctly, it almost never fails. Disagreements between theory and experiment usually signal missing details or overlooked effects, such as a stray magnetic field or a slight change in temperature, rather than a breakdown of the framework itself. Over time, physicists have refined and extended the theory, incorporating additional insights while preserving its core structure. The result is a body of knowledge that feels stable, even if its implications about the nature of reality can feel strange to the mind. It explains why matter has structure, why light behaves the way it does, and why the microscopic world supports the macroscopic one so reliably. There is a quiet comfort in this success. Quantum physics suggests that beneath the apparent solidity and chaos of the world lies a set of rules that accompany, insistent and universal. The same principles apply whether one is examining a single atom in a laboratory on Earth or the light arriving from a star billions of light-years away. And yet all that confidence is carefully scoped. Quantum physics excels when space and time behave as a steady, unmoving background. It assumes that distances are well defined, that time flows smoothly forward, and that the stage remains stable. Within those assumptions, it performs brilliantly. It is not a flaw for a theory to have boundaries. What matters is that those boundaries are understood and respected. For the most part, the universe cooperates with this division. The situations encountered in everyday life fit comfortably within this framework. Only by appreciating this immense success can we begin to see the true puzzle, that something as vast as gravity refuses to fit within such a dependable reach. While the quantum world thrives in the restless dance of the small, we must now shift our gaze to the silent, sweeping majesty of the large. Gravity is often introduced to us in childhood as a simple pull, a magnetic-like tug that keeps our feet on the ground and causes the apple to fall from the tree with dependable enthusiasm. This description serves us well enough for the practicalities of everyday life, but as we look deeper into the architecture of the cosmos, we find that this familiar picture is a vast simplification. Gravity is not merely a force reaching across a void to grab hold of distant objects. It is something far quieter, deeper, and more expansive in its character. In our modern understanding, gravity is how space and time themselves respond to the presence of mass and energy. This profound shift in perspective comes from general relativity, the framework that describes the universe on its grandest scales. In this view, space is no longer an empty passive stage where events happen. Time is no longer a uniform universal clock ticking identically for everyone everywhere. Instead, space and time are woven together into a single flexible fabric, a connected structure that is both responsive and dynamic. Mass and energy do not merely exist within this fabric, they determine its very geometry. When a massive object like a star or a planet is present, the fabric of spacetime bends and curves around it. What we perceive as the force of gravity is actually just the natural motion of objects following the curves of this warped landscape. A planet orbiting a sun is not being held in place by an invisible ghostly tether or a string of force. Instead, it is simply following the straightest possible path through a region of space that has been gently curved by the sun's immense mass. From the perspective of the planet, there is no pull at all. The motion feels effortless and natural because the curve is built into the very environment it moves through. This idea of gravity as geometry changes everything we thought we knew about the universe's container. It suggests that the stage is inseparable from the actors, and the story being told is written into the very dimensions of reality. This is the geometry of the immense, a language of smooth surfaces and continuous flows that governs the motion of everything from a drifting satellite to the collision of distant galaxies. The consequences of this geometric view are as concrete as they are poetic. Because space-time is flexible, light passing near a massive object cannot travel in a perfectly straight line. It must follow the contours of the warped space, bending its path as it grazes the edge of a star. Clocks, too, are affected by this geometry. Time itself flows at a different rate, depending on how deep one sits within a gravitational curve. A clock placed at the base of a high mountain will tick ever so slightly slower than a clock placed at its peak, because the mass of the Earth curves more strongly closer to its center. While these effects are far too small for our human senses to detect in our daily routines, they are real, measurable, and essential. Without accounting for these subtle shifts in the flow of time and the bending of space, the navigation systems we rely on would lose their accuracy within minutes. Gravity is not a distant abstraction. It is the invisible hand that coordinates the rhythm of the physical world, ensuring that the large-scale universe evolves with a sense of calm and predictability. What makes gravity feel especially different from the flickering quantum effects of the small is its characteristic scale and its inherent smoothness. Gravity does not rush. It does not flash in and out of existence or jump between allowed states. It accumulates slowly and acts with a relentless, patient persistence. A single subatomic particle has almost no gravitational influence at all. Its mass is too small to leave a meaningful dent in the fabric of space-time. But as matter gathers, as dust becomes rocks and rocks become planets and planets become stars, the influence of gravity builds. It is a collective force, a steady summation of every gram of matter in existence. Unlike the interactions of the quantum world, which arrive in discrete packets or quanta that can be isolated and counted, there is no known smallest unit of gravity in our current observations. Its effects blend smoothly from one point to the next, forming gentle gradients of curvature rather than sharp, jagged transitions. This continuity is why the large-scale universe feels so stable. Orbits repeat for billions of years without stuttering. Stars burn through their lifespans guided by a steady hand. The evolution of the cosmos is a long, slow story told through the gradual deepening and shifting of spacetime's curves. Mass and energy both play a role in this grand shaping. It is a common misconception that only solid matter creates gravity, but in the language of the immense, anything that carries energy contributes to the curvature of the universe. Light, pressure, the motion of particles, and even the energy stored in the vacuum of empty space all play a role in telling spacetime how to bend. This broad sensitivity gives gravity a truly universal quality. It does not discriminate between types of matter or charge. It does not switch off or fade away abruptly at long distances. Its influence extends across the entirety of the void, growing weaker as objects separate but never truly vanishing. Because of this, gravity is the master architect of the largest structures ever observed by human eyes. It is the reason gas and dust gradually collect into the nurseries of stars. It is the reason hundreds of billions of stars assemble into the spiral arms of galaxies. It is the reason galaxies themselves are drawn together into vast clusters and filaments that stretch across hundreds of millions of light years, outlining a cosmic web that defines the limits of the observable world. There is a certain patience to gravity's work that sets it apart from the frenetic, probabilistic activity of the quantum world. While quantum effects dominate the busy, high-energy interactions of particles, gravity shapes the long-term history of the universe. It governs the rise and fall of celestial bodies and the overall expansion of space itself. At the heart of this description lies a relationship between structure and substance. Mass tells space how to curve, and space tells mass how to move. This replaces the old notion of force with a dialogue between container and contained. Gravity is not something that happens within space and time, it is something that happens to space and time. This distinction explains why gravity is so difficult to treat as just another interaction. It defines the background upon which everything else occurs. It is not a guest at the party, it is the floor, the walls, and the ceiling. It is the very stage that provides the context for existence, even in extreme environments, where the curvature of space-time becomes incredibly steep. Gravity maintains its sense of continuity. Near a dense object like a neutron star, space bends sharply and time slows noticeably. Yet the transition from the flat space of the void to the deep well of the star remains a smooth, unbroken slope. There are no abrupt jumps, no sudden flickers of state, and no uncertainty in the path an object will take. This fluid nature stands in quiet contrast to the grainy, pixelated reality of the quantum realm, where change comes in steps and outcomes are gambles of probability. Gravity does not gamble, it unfolds. It represents a world of certain trajectories and predictable futures. Understanding gravity as the geometric shaping of reality allows us to see the universe as a unified whole, a single fabric stretching from the beginning of time to the furthest edges of the future. It provides the stability that allows life to exist and the regularity that allows science to flourish. Yet, it is precisely this calm, smooth, and universal nature that makes it so resistant to the jumpy rules of the small. Gravity is the whisper of the infinite, a force that shapes the architecture of the cosmos with a silence that masks its true complexity. Modern physics rests upon two sturdy pillars, each reliable, each tested to a degree of precision that borders on the miraculous, yet they do not speak to one another in a language that makes sense. The oddity we face in our quest to understand the universe is not that these theories exist, but that they appear to describe two different realities while claiming to govern the same single world. Imagine, if you will, having two maps of the same vast landscape. One map is designed with incredible detail to navigate the bustling streets of a city, showing every sidewalk, every doorway, and every flickering street lamp. This is the quantum map. The other map is a topographical masterpiece, designed to chart the movement of continents and the slow, sweeping curves of mountain ranges. This is the gravitational map. Both maps are accurate. Both are internally consistent. Travelers have used both for decades to reach their destinations without fail. And yet, if you were to place one map directly on top of the other, you would find that the coordinate systems do not overlap. The lines do not meet. Placing them together produces confusion rather than clarity, as if the universe were being viewed through two different lenses that refuse to focus at the same time. The mismatch between these two maps is not a result of carelessness or a lack of imagination on the part of scientists. It is a fundamental disagreement about the nature of the stage upon which the drama of existence unfolds. Quantum physics assumes a background stage, a fixed and stable arena of space and time where particles move, interact, and exchange energy. In the quantum view, space and time are like the floor and walls of a theater. They provide the setting and the framework, but they are not part of the play. They are quietly taken for granted, remaining passive and unchanging while the actors perform their intricate dances. The rules of the quantum world describe what happens on that stage, not how the stage itself behaves. Gravity, however, does the opposite. In the language of general relativity, space and time are not a passive backdrop or a hollow container. They are active, dynamic, responsive participants. They are the fabric of the story itself. The stage in the gravitational map is not made of solid wood or stone. It is more like a fluid or a flexible sheet that stretches, curves, and evolves in response to the presence of mass and energy. This leads to a profound conceptual conflict that sits at the very core of our understanding. Quantum physics is built on the idea of discreteness, the notion that everything can be broken down into individual, countable pieces. It views the world as a collection of grains, where energy and matter arrive in specific packets and interactions happen in sudden jumps. Gravity, by contrast, is a theory of continuous and smooth. It describes the universe in terms of flowing fields and gentle gradients of curvature. It does not recognize the concept of a pixel of space or a quantum of time. In the gravitational world, you can always zoom in further and find a smoother surface, a smaller curve, a more gradual transition. When we try to force the jumpy, granular rules of quantum mechanics onto the smooth, fluid fabric of space-time, the mathematical language we use to describe the universe begins to break down. The equations start to produce answers that are physically impossible, such as infinities that suggest a single point contains an endless amount of energy. It is a sign that the two maps are using different dialects to describe the same truth, and we have not yet found the master dictionary that can translate between them. What makes this situation especially strange is that nature does not appear to recognize this division. There is no clean, visible boundary in the physical world where one theory politely steps aside and allows the other to take over. The same subatomic particles governed by the flickering rules of quantum physics also possess mass and energy, which means they must, in principle, influence the curvature of space and time. Likewise, the same space and time shaped by the massive weight of stars must have an effect on the behavior of the particles moving through it. In practice, physicists have managed to manage this duality by simply using each theory where it works best. We use quantum physics to build computers and understand the glow of a LED, and we use gravity to navigate spacecraft and predict the path of an eclipse. Most of the time, this separation works beautifully because atoms are too light to noticeably curve space, and planets are too large to display quantum fuzziness. The universe allows this division to persist without obvious contradiction in our daily lives, as if it is keeping its two sets of books separate to avoid an audit. But the division itself is peculiar and increasingly difficult to ignore for those who seek a deeper truth. Reality does not come with labels announcing when one set of rules applies and another does not. There is only one universe unfolding across all scales at once, from the vibration of a string to the expansion of a galaxy. That it requires two incompatible descriptions to be understood feels less like a design feature and more like a significant clue that something deeper and more fundamental is missing from our picture. This tension suggests that the universe may be far richer and more complex than any single framework can capture on its own. It hints at the existence of a hidden layer of reality, a more basic language from which both gravity and quantum physics emerge as approximations. Just as the appearance of a smooth ocean is actually the result of countless individual molecules moving together, perhaps the smooth space-time of gravity and the grainy particles of quantum physics are both different expressions of a deeper, unified structure we have yet to fully perceive. For now, physics lives comfortably within th duality, a state of affairs that works well enough to describe almost everything, while quietly reminding us that almost everything is not quite the same as everything. We are like explorers who have successfully mapped the coastlines of two different continents but have yet to find the ocean that connects them. There is a certain humility in this realization, a recognition that even our most successful ideas have their limits. The mismatch between our two great theories is not a failure of intelligence, but an invitation to curiosity. It is the place where the mystery of the universe remains most vibrant, a gap where the known ends and the truly new might one day begin. As we rest tonight, we can find comfort in the fact that the universe is not yet a closed book. It still guards its secrets, waiting for us to develop the eyes to see and the language to describe the unity that must surely exist beneath the surface of our divided maps. The path toward that unity is long and requires a patience that mirrors the slow evolution of the cosmos itself. It is a journey that progresses not through strength or aggression, but through the quiet refinement of our questions and the willingness to let go of what we think we know. By noticing where our perfectly good ideas no longer fit together as neatly as expected, we gain a better sense of where the boundaries of our current understanding lie. The tension between the smooth and the grainy, the large and the small, the stage and the actor, is the very heartbeat of modern inquiry. It keeps the field of physics alive and breathing, ensuring that we never become too comfortable with our existing explanations. In the quiet hours of the night, as the world settles into a rhythmic stillness, we can allow ourselves to inhabit that gap. We can let the contradictions exist without needing to resolve them immediately. We can appreciate the precision of the street map and the majesty of the mountain map, knowing that somewhere, in a place we have yet to reach, they both describe the same beautiful and unified landscape. To truly understand the friction between the two great pillars of physics, one must immerse themselves in the sheer unceasing activity of the quantum realm. If the world of gravity is a calm and steady ocean, the microscopic world is a torrential rain falling onto a restless surface where nothing ever truly stands still. This is the realm of the restless microscopic world, a place where the very concept of nothingness is challenged by a reality that is constantly fluctuating, vibrating, and transforming. At these scales, the solidity we take for granted in our daily lives, the firmness of the chair beneath you, the cool glass of a window, the steady weight of a book, dissolves into a frantic swarm of activity that is as beautiful as it is chaotic. Quantum physics reveals that if we were to zoom in far enough, past the cells, past the molecules, and deep into the heart of the atom, we would find that matter is not made of tiny solid lumps, but is instead a manifestation of fields that are never entirely at rest. Even in what we call a vacuum, space is not truly empty. It is a sea of potential, where pairs of particles and antiparticles are constantly winking into and out of existence, appearing for a fraction of a second before vanishing back into the void. This restlessness is not a sign of disorder, but a fundamental property of the universe. It is governed by a principle that suggests there is a limit to how much we can know about a system at any given time. In the macroscopic world, we are used to knowing exactly where something is and exactly how fast it is moving. You can watch a car driving down a street and measure its position and its speed simultaneously with perfect clarity. Thank you. But in the microscopic world, the universe imposes a strict budget on information. The more precisely you try to pin down the location of a particle, the less you can know about its momentum, and vice versa. It is as if the universe is deliberately keeping its deepest details slightly out of focus, maintaining a level of fuzziness that prevents the smallest pieces of reality from ever being frozen in place. This inherent uncertainty means that a particle does not exist at a single point. Instead, it exists as a cloud of possibilities, a wave of probability that only collapses into a single location when it is forced to interact with the larger world. This is the grainy texture of reality that sits in such stark contrast to the smooth, flowing geometry of gravity. In this restless world, the very idea of a path becomes something strange. In our everyday experience, an object moves from point A to point B along a single, definite trajectory. But a quantum particle, in its restless state, seems to explore all possible paths simultaneously. It is as if the particle is aware of every potential route it could take and only chooses one at the final moment of interaction. This behavior is what allows electrons to exist in the shells around an atom without crashing into the nucleus. They are not like little planets orbiting a sun. They are more like standing waves of probability, vibrating at specific frequencies. These vibrations are what give matter its structure and volume. The reason you cannot push your hand through a solid table is not because the table is packed with solid material. It is actually mostly empty space. You are stopped because the restless electrons in your hand and the restless electrons in the table are vibrating in such a way that they repel each other, creating a firm boundary where there is no actual solid matter to be found. Everything touch is a result of this microscopic, energetic resistance. This constant motion is also what allows for the phenomenon of quantum tunneling, a process that feels like magic but is essential for the universe to function. In the classical world, if a ball does not have enough energy to roll over a hill, it will simply roll back down. But in the restless microscopic world, because particles are spread out as waves of probability, there is a small chance that a particle can simply appear on the other side of a barrier, even if it doesn't have the energy to go over it. It tunnels through the obstacle. This is not just a theoretical curiosity, it is the reason why the sun is able to shine. Inside the core of a star, protons repel each other with immense force. Under classical rules, they would never get close enough to fuse together. But because of the restless, uncertain nature of the quantum world, they are able to tunnel through that repulsion and fuse, releasing the energy that lights up the cosmos. Our very existence and the warmth of the sun on our skin is a direct gift from the restlessness of the small. As we dwell on this activity, it becomes clear why gravity finds it so hard to join the dance. Gravity is a theory that relies on the idea that space and time are smooth and continuous, like a perfectly stretched sheet of silk. But the quantum world suggests that if you look closely enough at that silk, you would find it is made of individual, vibrating threads that are constantly twitching and jumping. When physicists try to apply the rules of gravity to these restless quantum fields, the math begins to scream. The equations attempt to account for every tiny vibration, every flicker of energy, and every momentary particle. Because there is no limit to how many of these fluctuations can occur in a small space, the energy levels in the calculations begin to pile up until they reach infinity. In the world of physics, an infinity in a calculation is usually a sign that the theory is being asked to do something it wasn't designed for. It is like trying to use a magnifying glass to look at a digital image until you only see the pixels. The picture of the whole is lost in the noise of the parts. The restlessness of the microscopic world also means that time and space themselves might be subject to these same fluctuations. If everything else is jumpy and discrete, it is possible that at the very smallest scales far below what any microscope could ever see, space and time themselves might lose their smoothness. This is a concept often called quantum foam. In this speculative vision, if we could zoom in to the most extreme degree, we would see spacetime not as a steady background, but as a bubbling, turbulent froth of geometry, where the very concepts of before and after, or here and there, become blurred and entangled. This is the ultimate expression of the restless world. It is a level of activity that gravity, in its current, elegant form, simply cannot describe. Gravity expects a world that moves in predictable curves, not one that bubbles and froths like a stormy sea. Despite this chaos, there is a profound sense of harmony in the microscopic world. The restlessness is not random. It follows the strict and beautiful laws of quantum mechanics. It is a world of incredible order, hidden behind a mask of uncertainty. The transitions of electrons, the spin of subatomic particles, and the exchange of energy packets all occur with a precision that allows us to build the most advanced technologies in history. We have learned to harness this restlessness, steer it, and use it to our advantage. Every time you use a smartphone or look at a high-definition screen, you are interacting with the controlled restlessness of billions of quantum particles. We have mastered the small, yet the large remains a distant, silent observer. As the night deepens, we can appreciate the contrast between these two worlds. There is the vast, silent and curved universe of the stars, governed by the patient geometry of gravity, and there is the hidden, vibrating and restless world of the atom, governed by the flickering rules of the quantum. We live in the middle, a place where these two extremes meet but do not yet merge. We are made of the restless small, but we are held together by the patient large. Understanding this duality is perhaps the most important step in our journey. It reminds us that reality is multi-layered and that truth can be found in both the silence and the swarm. As you drift towards sleep, let the image of this restless world fade into a gentle hum. Imagine the atoms within you vibrating with a quiet, steady purpose, and let the chaos of the small settle into the calm of the large. The universe is a vast and intricate symphony, and though we may only hear a few notes at a time, the music is constant, reliable, and deeply beautiful. If the microscopic world is a frantic storm of activity, then gravity is the great stillness that eventually calms the waters. It is the patient hand that waits for the flickering of particles to average out, for the noise of the quantum foam to settle, and for the vastness of the cosmos to assert its long-term will. While the quantum world is preoccupied with the immediate, the sudden, and the probable, gravity is concerned with the enduring, the inevitable, and the structural. It is the power of long view. To understand the patient hand of gravity, one must look away from the jittery behavior of individual atoms and toward the silent, slow evolution of the stars and the spaces between them. Gravity does not care for the individual fluctuations of a single electron. It waits for the collective mass of a trillion particles to combine into a single, unified purpose. This is why gravity feels so different to our human senses. It is a force that requires patience to observe, as it builds its influence over millions of years, sculpting the vacuum of space into a home for light and life. One of the most remarkable features of gravity is that it is remarkably weak, yet it is the only force that truly dominates the large scale. This is a paradox of the universe. Compared to the electrical forces that hold your atoms together, gravity is almost non-existent. A simple toy magnet can pull a paperclip upward, easily defying the gravitational pull of the entire planet Earth. On the scale of a single particle, gravity is so faint that it is virtually undetectable. Yet gravity has a quality that the stronger forces lack. It is purely additive and universal. Every speck of mass, no matter how small, adds its own tiny curve to the fabric of space-time. While electrical charges can be positive or negative, cancelling each other out and leaving most large objects neutral, gravity only ever pulls in one direction. It never cancels, it only accumulates. It is like a slow, steady tide that rises so gradually you do not notice it until the entire landscape has been submerged. This accumulation is what allows gravity to reach across the void of space and hold galaxies together, even while it remains the weakest whisper at the level of the atom. Gravity's patience is best seen in the way it builds the universe from the bottom up. In the early ages of the cosmos, the universe was little more than a vast, cooling mist of gas. Had it been governed only by the frantic rules of the quantum world, that mist might have remained a disorganized cloud forever. But gravity was there, waiting in the silence. It began to pull at the slightly dense regions of gas, drawing them together with a touch so light it took millions of years to show progress. Slowly, those clouds became heavy. They began to collapse under their own weight, their centers growing hot and dense. Gravity did not rush this process. It allowed the compression to happen over eons until finally the pressure was so great that the first stars ignited, bringing light to the darkness. This same patient hand continues to guide each star's life. It balances the outward pressure of nuclear fusion with its own inward pull, maintaining a delicate stability that can last for billions of years. Our own sun exists in this state of graceful equilibrium, held together by gravity's tireless, steady grip. Unlike the quantum world, which seems to thrive on a kind of digital yes or no logic, gravity operates on the logic of the continuous and the analog. There is no point where gravity suddenly switches on or off. If you move twice as far away from a planet, its pull becomes 4 times weaker, but it never reaches zero. It simply thins out, stretching across the universe like an invisible silk thread that never quite breaks. This continuity is essential for the stability of the large-scale world. It allows for the predictable repeating cycles of the seasons and the reliable paths of the planets. It ensures that the atmosphere of our world remains tucked safely against the surface, allowing us to breathe. Gravity is the silent guarantor of our environment. It does not demand energy to function. It is simply a consequence of existing within the geometry of space. It is the weight of your body against the mattress, the fall of a leaf, and the motion of the moon, all parts of a single, smooth and unbroken curve. In the patient hand of gravity, time itself becomes a flexible and local experience. We are used to thinking of time as a universal constant, a river, that flows at the same speed for everyone. But gravity reveals that the river of time flows slower where the curvature of space is deeper. Near a massive object, time is stretched. This is not a trick of the mind or a flaw in our clocks. It is a fundamental property of the universe. A clock sitting on a planet's surface will tick slower than a clock floating in the deep void between stars. This suggests that gravity is not just pulling on matter, it is pulling on the very moments of our lives. It tethers time to mass, creating a universe where every location has its own unique rhythm. This slowing of time is gravity's way of asserting its dominance over the restless world. Where the quantum world wants to speed up and fluctuate, gravity slows things down, pulling reality into a deeper, more enduring state of being. There is also a profound sense of destiny in gravity's work. Because it is always attractive, gravity is the force that eventually brings the story of any structure to a close. It is the force that will eventually cause galaxies to collide and clusters to merge. It is the force that leads to the creation of black holes, those regions where gravity's patience has finally reached its ultimate conclusion, folding space so tightly that not even light can escape the curve. Yet even in these extremes, gravity remains a quiet and orderly architect. It follows the laws of geometry with absolute fidelity. It does not play dice with the positions of the stars. It provides the framework within which all other events must take place. Without the patient hand of gravity, the universe would have no structure, no history, and no home for the complex chemistry of life. We are the children of this pull, evolved to live and move within its constant embrace. As we consider this silent force tonight, we can feel a sense of relief in a world that often feels fast, fragmented, and uncertain. Gravity is the one thing that never wavers. It is the ultimate constant. It is the reason we can trust the ground to be there when we step, and the reason the stars will be in their familiar places when we look up. Gravity is the universe's way of providing a sense of place. It anchors us to our world and our world to the sun. It is a force of connection, a silent thread that binds every atom in your body to every star in the sky. By understanding its patient nature, we can begin to see why it refuses to be rushed into the flickering, jumpy box of quantum physics. Gravity is too big, too slow, and too deep for the rules of the small. It belongs to the architecture of the whole, a force that shapes the stage so that the quantum actors have a place to perform. Now, as the night settles deeper, imagine the Earth beneath you as a vast, gentle curve in the fabric of the universe. Feel the way gravity quietly holds you, not with a harsh grip, but with a steady and nurturing presence. Let your thoughts slow down to match the stars' pace. The atoms that make up your body were once forged in the hearts of stars, brought together by this very force over billions of years. You are part of gravity's long, patient story. There is no need to solve the mysteries of the universe tonight. It is enough to exist within them, to feel the weight of the world, and to trust in the steady, silent geometry that keeps everything in its proper place. The universe is in no hurry, and neither are you. Let the patient hand of gravity guide you toward a deep and restorative rest, as the curves of space-time cradle you in the quiet of the cosmic night. In the quiet chambers of the physical world, there is a hierarchy of power that remains hidden from our human senses, a vast disparity that physicists often call the hierarchy problem. To understand the tension between the two great pillars of the universe, one must first recognize that gravity is not a loud or assertive force. Despite its ability to move planets and anchor galaxies, gravity is, in fact, an incredible whisper in a crowded room, a presence so delicate that it is almost drowned out by the noise of everything else. If the universe were a grand orchestra, the other fundamental forces, the ones governing electricity, magnetism, and the binding of the atom, would be the brass and the drums, sounding with a volume that fills every corner of the stage. Gravity, by comparison, would be a single soft flute playing from the back of the hall, barely audible unless the rest of the music falls into a complete and total silence. This great imbalance is one of the most mysterious features of our reality, and it is a primary reason why we struggle to see how the small and the large are meant to fit together. When we think of the forces of nature, we tend to group them as equals, but the truth is far more lopsided. There are four fundamental interactions that govern everything we know. There is the strong nuclear force, which acts like a powerful glue to hold the centers of atoms together. There is the weak nuclear force, which handles the subtle transformations of particles and certain types of radioactive decay. Then there is the electromagnetic force, which is the architect of light, chemistry, and the solid feel of the world. And finally, there is gravity. If you were to compare the strength of the electromagnetic force to gravity at the scale of a single particle, the difference would be a number so large it exceeds our ability to visualize it. Electromagnetism is approximately 10%, followed by 36 zeros times stronger than gravity. This is a margin of power that is almost impossible to grasp. It means that the tiny electrical signals in your brain, or the simple static charge on a ball, are vastly more powerful than the gravitational pull of the entire mass of the Earth, when viewed through the lens of a single atom. You can see this imbalance in action with a simple experiment in your own home. If you take a small magnet and use it to lift a steel paperclip off a table, you are witnessing a victory for the underdog. That tiny handheld magnet is pulling the paperclip upward using the electromagnetic force. Opposing that magnet is the entire planet Earth, with its trillions of tons of rock, metal, and water, all pulling the paperclip downward with its cumulative gravity. And yet, the small magnet wins. It lifts the clip effortlessly. The collective gravitational might of an entire world is defeated by a piece of magnetized metal no larger than a coin. This is because gravity is so staggeringly weak that it requires an entire planet's worth of mass just to exert a pull that we can feel. At the level of individual particles, gravity is so faint that it effectively disappears. In the laboratories where physicists study the quantum world, gravity is often ignored entirely because its influence is so small that it sits far below the threshold of even our most sensitive measurements. This extreme weakness is why quantum physics can afford to be indifferent to gravity for most of its history. When an electron interacts with a proton inside an atom, the electromagnetic force between them is so dominant that gravity might as well not exist. It is like trying to measure the weight of a single eyelash while standing in the middle of a hurricane. The hurricane of the other forces is so loud and frantic that the whisper of gravity is simply lost in the noise. This is the crowded room of the microscopic world. It is a place filled with the high-energy chatter of particles swapping energy and shifting states. Because gravity is so quiet, it does not demand to be included in the quantum rulebook. For decades, this allowed scientists to build a nearly complete picture of the subatomic world without ever needing to account for the curvature of space or the flow of time. They could treat the stage as flat and fixed because the whisperer was too quiet to tell the stage to move. But the mystery of the imbalance remains. Why is gravity much weaker than all? Some theorists suggest that perhaps gravity isn't actually weak at all, but that its strength is being diluted. They imagine that our universe might have extra dimensions hidden from our view, and that while the other forces are trapped on our three-dimensional sheet, gravity is the only one capable of leaking out into those other dimensions. In this view, we only experience a tiny fraction of gravity's true power, like hearing a loud conversation through a very thick and heavy wall. Others wonder if weakness is a necessary condition for life itself. If gravity were even slightly stronger, stars would burn through their fuel in a few million years rather than billions, leaving no time for planets to form or life to evolve. If gravity was stronger, the universe might have collapsed back in on itself long ago. Its weakness is the very thing that gives the cosmos its vastness and its patience. This imbalance also explains why gravity only becomes the master of the universe when things get very large. Because the other forces can cancel each other out. Positive charges meeting negative charges to create neutrality, they eventually lose their reach. Once you have a large enough pile of matter, the electrical forces settle down and go quiet. But gravity, we have seen, never cancels. It only adds up. It is the only force that is always on, always pulling, and always reaching further. Eventually, if you gather enough mass together, the whisper of a trillion atoms becomes a roar. This is how gravity finally takes control, turning the chaotic mist of the early universe into the orderly structure of galaxies. It wins not through strength, but through persistence and the fact that it has no opposite. It is the only force that plays the long game. However, this transition from a whisper to a roar is exactly where the conceptual problem lies. We have one set of rules for the loud forces of the small, and another set of rules for the quiet force that governs the large. Because gravity is so weak, we have never been able to observe it behaving in a quantum way. We have never seen a packet of gravity or a single gravitational interaction between two particles. We are forced to infer how it might behave based on the rules of the other forces, but those rules were designed for a different scale of power. Trying to use the math of the strong and loud forces to describe the weak and quiet force of gravity is like trying to use a heavy industrial crane to pick up a single grain of sand. The tool is simply too blunt for the task, and the result is often a breakdown of the logic we rely on. As you reflect on this great imbalance, you can feel the strange, lopsided beauty of the universe. We live in a world where the most powerful things, the atoms that make us up, are governed by forces of incredible strength, yet we are held to our planet by a force so weak it can barely be measured at the scale of a particle. We are caught between the roar of the small and the whisper of the large. This disparity is not a mistake. It is the very thing that allows for the complexity of the world. It creates a separation of scales that lets chemistry happen in one corner while galaxies form in another, without them interfering with each other too much. It provides a buffer, a space for the universe to breathe and grow. Tonight, as the silence of your rooms surround DSU, let yourself become aware of that soft gravitational flute playing in the background. It is the pull of the Earth, a force so weak it cannot even lift a paperclip against a tiny magnet, yet strong enough to keep the moon in its orbit and the atmosphere around our world. It is a gentle, persistent reminder of your connection to the cosmos. You do not need to understand why it is so quiet, you only need to feel its presence. Let the imbalance of the world bring you a sense of peace, knowing that the most important forces are often the ones that do not need to shout. The universe is balanced on a razor's edge of strength and weakness, and you are resting safely in the middle of it all. Scale matters in physics because the universe behaves very differently depending on how closely it is examined, and this variation creates a natural buffer that keeps our reality stable. What feels solid and predictable at one level can become strange and uncertain at another, yet these layers rarely interfere with one another in our daily lives. Laws that describe motion perfectly well for planets begin to fail for particles, and rules that govern atoms say almost nothing about the behavior of galaxies. Reality does not change its fundamental nature from moment to moment, but the way it presents itself shifts dramatically with size, distance, and mass. This sensitivity to scale is not a flaw in our understanding of physics, it is a feature of the universe itself. Nature does not offer a single, flat set of behaviors that applies equally everywhere. Instead, different patterns emerge depending on whether our attention is focused on the very small, the very large, or the wide spaces in between. Physics, as a result, has learned to speak in different dialects, each tuned to a particular range of scales, and it is the distance between these ranges that acts as a protective buffer for the cosmos. At the smallest scales, quantum effects dominate the conversation completely. Here, particles do not behave like tiny versions of everyday objects. They spread out, they interfere with themselves, and they occupy allowed conditions rather than arbitrary ones. Interactions happen in discrete steps, and outcomes are described by probabilities rather than certainties. At this level, gravity is so weak that it barely enters the conversation at all. Inside atoms, the forces shaping behavior are overwhelmingly quantum in nature. Electrons respond to electromagnetic influences that are unimaginably stronger than gravity, creating the structure of matter and the rules of chemistry. Gravity is certainly present, but its influence is so faint that scientists can ignore it without any real consequence to their calculations. The quantum world does not need gravity to explain its everyday workings, just as a swimmer in the ocean does not need to account for the movement of the tectonic plates beneath the seabed to stay afloat. At the opposite extreme of the buffer, gravity takes over with a slow and steady authority. When dealing with planets, stars, galaxies, and the large-scale structure of the universe, quantum effects fade into the background noise. Individual particles no longer matter in the grand tally, only their collective mass counts. Gravity accumulates, sculpting orbits and governing the expansion of space itself. At these scales, the smooth curvature of space and time dominates behavior, and the frantic quantum fluctuations of individual atoms average out until they become negligible. Between these two extremes lies the wide middle ground where human life unfolds. This is the realm of the buffer of scale. Objects here are large enough for gravity to be noticeable, giving us weight and keeping the moon in the sky, yet they are small enough for the strange quantum effects to remain hidden from our eyes. A falling cup obeys classical motion. A thrown ball follows a predictable arc. Buildings remain standing, and materials behave reliably. The world feels stable and intuitive because the scales involved allow gravity and quantum effects to stay politely out of each other's way. This separation by scale is remarkably effective, and serves as a kind of natural peace treaty between the two theories. Quantum physics handles microscopes, gravity handles space. For most practical purposes, the boundary between them is clean and well-defined. Each theory can be applied where it works best, and the results are accurate enough to build advanced technology, navigate the vastness of space, and describe the long history of the universe. The difficulty only arises in those incredibly rare situations where scale forces the two to meet. Such situations require enormous amounts of mass to be compressed into extraordinarily small regions or distances to be shrunk to extremes far beyond anything we encounter. In these rare environments, gravity becomes strong enough that its effects can no longer be ignored at the small scale, while quantum behavior remains unavoidable because of the sizes involved. Outside these exceptional cases, nature keeps the two regimes separate. Atoms do not curve space in any noticeable way, and galaxies do not behave like fuzzy quantum objects. The universe offers very few places where both descriptions are required at once, which is perhaps why the underlying conflict remained hidden for so long. This rarity helps explain why the problem of unification took decades to fully reveal its true depth. For a long time, physicists could work comfortably within one framework or the other without ever feeling the need to bridge the gap. Quantum theory flourished in laboratories, explaining the glow of gases and the behavior of metals. Gravity guided the hands of astronomers and cosmologists as they mapped the heavens. Each theory solved the specific problems it was designed to address, and neither demanded immediate reconciliation with its counterpart. There was no everyday experiment screaming that something fundamental was wrong. No household object behaved in a way that required both quantum rules and strong gravity to be explained. The mismatch remained tucked away in the extreme corners of the universe, such as the centers of black holes or the very first moments of the Big Bang, places that were difficult, and sometimes impossible, to probe directly. In this sense, scale acted as a kind of natural buffer, a gift that allowed physics to progress rapidly without forcing a premature confrontation between incompatible ideas. There is also a psychological aspect to this delay in our understanding. Human intuition is shaped entirely by the middle scales of experience. We live in a world where gravity is a gentle, constant presence and quantum effects are functionally invisible to the naked eye. It feels natural to think in terms of smooth motion, solid objects and definite locations. The idea that reality behaves very differently at other scales can be accepted intellectually, but it does not demand our constant attention because it does not affect how we move through the world. As a result, the places where the theories truly clash felt distant and abstract for a long time. They were distant curiosities that did not interfere with building machines, predicting chemical reactions, or sending spacecraft to other planets. Only as our observations improved and our telescopes became more powerful did the tension become harder to ignore. We began to see environments where gravity grows extreme, and hints of limits in our existing descriptions started to emerge. Even so, the separation by scale remains one of the universe's most effective disguises. It hides the deep disagreement between quantum physics and gravity behind a vast range of conditions where each theory works beautifully on its own. Most of the time, the universe behaves as though it has chosen sides, allowing one framework to dominate, while the other remains a silent observer. This makes the problem of unifying them feel oddly detached from our everyday reality. It is not a crack that spreads visibly across the surface of physics like a break in a window. Instead, it is a fault line buried deep beneath layers of successful explanation. Understanding the role of scale helps make this less mysterious. The theories do not fail because they are careless, they fail to meet because the universe rarely asks them to operate together. Nature itself enforces the separation, keeping quantum effects small where gravity is strong, and gravity weak where quantum effects dominate. That separation has been a boon to human knowledge growth. It allowed physics to grow, mature, and succeed across an enormous range of phenomena without being paralyzed by its own internal contradictions. It delayed the moment when the deep tension had to be faced, giving us time to master the individual pieces before trying to solve the whole puzzle. Now, as our attention turns increasingly toward the edges of what can be observed, scale no longer hides the problem as effectively as it once did. The rare places where both descriptions should matter begin to feel less like exceptions and more like vital clues. They suggest that the universe has been quietly accommodating two different ways of speaking about reality, each suited to a different range of scales, while waiting for us to find the deeper language that can describe them both at once. Tonight, as you rest, you can appreciate the stability this buffer offers. You are safe in the middle ground, where the world is predictable and the laws of nature are steady. Let the vastness of the cosmic scale and the intricacy of the microscopic scale exist in the background, knowing that the buffer of scale is holding them in a perfect, silent balance just for you. Trouble begins not when either theory is used on its own, but when they are asked to speak to each other in the same mathematical breath. Each framework is internally consistent, carefully tested, and remarkably successful within its own domain. The difficulty arises when physicists try to apply both sets of rules to the same physical situation and discover that they do not naturally align. At first, the attempt seems straightforward. Quantum physics has a well-established way of describing interactions as the exchange of particles or the fluctuation of fields. Gravity has a well-established way of shaping the world through the geometry of space and time. In principle, one might expect that gravity could simply be treated as another influence within the quantum picture, or that quantum effects could be layered gently onto the curved geometry described by gravity. In practice, this expectation quickly dissolves into a mathematical nightmare. When physicists try to treat gravity as a quantum interaction, the calculations begin to behave strangely. Quantities that should remain finite and manageable instead grow without bound. Small corrections balloon into enormous nonsensical contributions. Predictions lose their connection to anything measurable or real. Mathematics does not merely become difficult, it stops making physical sense. This breakdown is not subtle. It is not about missing a single term or choosing the wrong approximation. The very structure of the calculation begins to unravel, producing infinities that cannot be removed without destroying the logic of the theory. To understand why these infinities awaken, it helps to remember what each framework assumes about the nature of the world. Quantum physics is built on the idea that all interactions take place against a fixed, unchanging background of space and time. Distances and durations are assumed to be well-defined and stable. The stage is set, the lighting is fixed, and the particles act upon it. Gravity, however, refuses this arrangement. In the gravitational description, space and time are not fixed containers. They respond dynamically to the presence of mass and energy. The stage itself moves, bends, and evolves alongside the actors. Trying to quantize gravity is therefore not like quantizing a force acting on a stage. It is like trying to quantize the stage itself. When these assumptions collide, the calculations lose their footing. quantum methods expect a stable ground that gravity simply does not provide. Gravitational descriptions expect a smooth geometry that quantum fluctuations disrupt with their jumpy, restless nature. Each framework pulls the mathematical structure in a different direction, and the result is a collapse into infinite values. These infinities are the universe's way of saying no, indicating that the way we are combining these ideas is fundamentally incompatible with how reality actually functions. Physicists have not been idle in the face of this problem. For decades, they have tried clever rearrangements, alternative formulations, and increasingly sophisticated tools to tame these runaway numbers. They have explored new ways of organizing calculations and new perspectives on what the fundamental ingredients of reality might be. They have developed techniques like renormalization, which worked beautifully to hide infinities in other areas of quantum physics. But gravity is different. It is non-renormalizable. Every time you fix one infinity, another, more powerful one takes its place. The same pattern keeps appearing whenever gravity is pushed fully into the quantum framework using familiar methods. The theory becomes unstable, the numbers refuse to settle, and the framework ceases to be predictive. This is not because gravity is especially messy or because quantum physics is poorly constructed. Both are elegant and beautiful in their own way. The difficulty lies in how deeply their assumptions are woven into their structures. Each theory encodes a different idea about what space and time are, and those ideas cannot simply be layered on top of one another like sheets of paper. There is a quiet kind of frustration in this realization. It is not the frustration of repeated failure, but the frustration of clarity. The problem is not hiding in some obscure corner. It reveals itself quickly and consistently, as though the universe is politely but firmly declining the invitation to merge these descriptions without something more fundamental changing first. One way to see this is to notice how each theory treats the concept of scale. Quantum physics expects that zooming in reveals finer and finer detail, a never-ending graininess. Gravity expects that zooming reveals stronger, more focused curvature. When both expectations are applied at once, the result is not a richer picture, but a clash of interpretations. The same region of reality is being described in two incompatible ways. This clash shows up mathematically as runaway behavior, where the tiny fluctuations of the quantum world interact with the curvature of gravity to create a feedback loop that spins out of control. Calculations that work beautifully for electromagnetism or the nuclear forces suddenly become uncontrollable when the geometry of space-time starts to vibrate along with the particles. Importantly, this does not suggest that either theory is wrong. Rather, their success elsewhere makes the failure to combine them even more striking. If either framework was sloppy or unreliable, the mismatch could be dismissed as a technical inconvenience or a sign of an unfinished draft. But both are among the most scrutinized ideas in the history of science. The refusal to cooperate, therefore, feels intentional in a way, not dramatic or defiant, but consistent. Gravity and quantum physics each insist on their own view of reality, and neither is willing to yield without a deeper revision of the underlying picture. This realization has shifted how physicists think about the problem. Rather than treating it as a matter of finding the right calculation, many now see it as a signal that something fundamental is missing. The issue may not be how gravity fits into quantum physics or how quantum effects fit into gravity, but how both emerge from a deeper framework that has yet to be fully recognized by our current instruments and minds. There is some humility in that perspective. It accepts that even our most successful and cherished ideas can have limits. It acknowledges that progress sometimes requires stepping back and questioning our foundations, rather than pushing forward with greater force. The difficulty of unifying these theories has helped clarify their unique strengths. By watching where they fail to overlap, physicists gain insight into what each one truly assumes about the universe. The mismatch becomes informative rather than merely obstructive. In this sense, the theory's refusal to cooperate is not an embarrassment, it is a guide. It points toward the places where our intuition needs revision, and where entirely new concepts may be required. The frustration that arises here is quiet and intellectual. It does not come from a lack of effort or imagination, but from repeatedly encountering the same structural barrier that the universe has placed in our path, No matter how carefully the problem is approached, the universe appears to be telling a consistent story, even if that story remains incomplete for now. Rather than forcing a resolution through sheer mathematical willpower, many physicists have learned to listen to that story more closely. The breakdown itself becomes part of the evidence. It suggests that space, time, and matter may be related in ways that neither framework fully captures on its own. When theories refuse to cooperate, it is tempting to see the situation as a dead end. But in physics, such moments often mark the edge of true understanding. They indicate that the language being used has ached its natural limits. Gravity and quantum physics do not argue loudly, they simply talk past each other. And in that quiet disagreement lies one of the deepest clues we have about the structure of reality. Tonight, as you feel the weight of your body and the stillness of the air, let the mystery of these infinities settle into the background. You do not need to resolve math to exist within the harmony of the universe. The world remains whole and stable, even if our descriptions of it are still searching for their final meeting place. Let your mind drift away from the numbers and toward the peace of the unknown. Black holes are the places where the universe stops being gentle, and where the separation of scales that usually protects our understanding finally collapses. The slow, patient curvature that guides the motion of planets and stars steepens dramatically in these regions, folding space and time inward with a relentless and singular focus. Matter falls, light bends, and paths that once led outward into the vastness of the cosmos curve back toward a central region from which there is no return. To our human eyes, these are not violent places in the sense of a storm or an explosion. They are quiet, dark, and profoundly patient. But within that calm and silent exterior, gravity reaches its most extreme expression. A black hole forms when enough mass is compressed into a small enough region that gravity overwhelms every other influence in nature, including the light itself. The result is not an object in the usual sense of a solid planet or a burning star, but rather a boundary in the fabric of reality, a surface known as the event horizon, beyond which the familiar rules of motion no longer allow for escape. From the outside, a black hole can appear deceptively simple, defined only by its mass, rotation, and charge. But inside that boundary, the story becomes far more complicated and far more significant for our understanding of the universe. What makes black holes especially important for the search to unify physics is not just their intensity, but the way they force different scales to interact. Near the heart of a black hole, gravity becomes extraordinarily strong on distances so small that quantum effects can no longer be ignored. Space curves sharply, and time slows to a crawl relative to the world outside. Here, the separation between the smooth, geometric world of gravity and the grainy, restless world of quantum physics begins to dissolve. This is precisely the kind of environment where the universe can no longer keep its two descriptions apart. In most places, as we have seen, gravity is too weak to disturb quantum systems, and quantum effects average out before gravity becomes noticeable. But near a black hole, that balance shifts. The curvature of space and time grows so steep that even the smallest details of matter and energy are caught in the warp. Quantum behavior becomes entangled with gravitational structure in ways that neither theory can fully describe on its own, turning the black hole into a natural laboratory for the most fundamental questions of existence. One of the first hints of this deep tension came from considering what happens at the very edge of this threshold. From a purely gravitational perspective, the boundary is calm, matter drifts inward, light grows dimmer as it struggles to climb out of the gravity well, and time slows down. But when quantum effects are considered, the picture becomes less straightforward. Quantum physics suggests that empty space is never empty. Even in total darkness, tiny fluctuations occur where particles briefly appear and vanish in pairs. Near the edge of a black hole, the immense gravity can pull these pairs apart before they have a chance to disappear. One particle falls into the dark, while the other escapes into space as a faint glow of radiation. This suggests that black holes are not perfectly black. They leak energy, and over vast periods of time, they may even evaporate. This discovery created a crisis in physics because it touched on the nature of information. If a black hole evaporates and disappears, what happens to the information about everything that fell into it? Gravity says it is lost. Quantum physics says information can never be destroyed. This disagreement near the black hole's threshold is where the cracks in our current understanding become most apparent. The tension does not announce itself with a loud bang or a flash of light. Instead, it is a quiet mismatch revealed through careful thought and subtle calculation. Black holes force physicists to confront questions that can be safely ignored elsewhere in the cosmos. They ask us what happens to an object's history when it is crushed. They ask us how space behaves when it is twisted into a knot. They ask us if time itself can be treated as a quantum entity that fluctuates and jumps. In this sense, black holes function like natural experiments set up by the universe, exploring regimes that we could never hope to recreate in a human laboratory. They compress mass and energy into configurations that push our best theories to their absolute limits, showing us exactly where the math begins to fail and where our intuition starts to falter. The imagery surrounding black holes in our culture often emphasizes destruction, but their role in the universe is much more foundational and anchored. They sit at the centers of almost all large galaxies, including our own, acting as gravitational anchors for hundreds of billions of stars. They influence the motion of gas and the birth of new stars over immense distances, shaping the environment around them slowly over millions ND billions of years. Their extremity is local, but their presence is enduring. This makes them ideal testing grounds for our ideas about reality, not because they are dramatic, but because they are persistent features of the landscape. They provide long-lived conditions where gravity remains extreme, allowing us to study how light bends around its edges and how space-time ripples when they collide. Every observation we make of these distant giants carries information about how gravity behaves under extreme stress, and every clue brings us closer to understanding the hidden link between the large and the small. Yet, even with our best telescopes and our most advanced math, black holes remain frustratingly opaque. Their interiors are hidden behind the veil of the event horizon, and their deepest regions cannot be seen or measured directly. Physics must infer what happens at the center by stitching together clues from the edges, knowing all the while that the resulting picture is incomplete. There is a certain humility built into studying black holes. They do not offer answers freely. They challenge our assumptions and reward our patience with even deeper mysteries. Rather than resolving the conflict between gravity and quantum physics, they sharpen it, making it impossible to ignore. This sharpening is valuable because it proves that the problem is not just an abstract or philosophical debate. It is a problem that exists in real physical objects that populate our universe. Black holes are not mere thought experiments. They are astrophysical realities that define the boundaries of what we know. In the quiet darkness near a black hole, familiar concepts begin to blur. Space behaves strangely, stretching and compressing in ways that defy our logic. Time behaves like a physical dimension that can be warped and slowed. The distinction between inside and out becomes subtle and complex. These are not just curiosities. They are signs that the language we use to describe reality is being pushed beyond its comfortable range. Black holes therefore occupy a special place in our journey. They are guides that show us where our theories strain and where new ideas are desperately needed. They expose the cracks in our knowledge, not by breaking the laws of physics, but by revealing where those laws seem to end. They are the ultimate frontier, a threshold between the known and the unknown that invites us to think differently about the nature of the stage we walk upon. As you rest tonight, imagine these silent giants scattered across the deep velvet of the cosmos. They are not monsters to be feared, but anchors of the universe, holding galaxies together with their invisible grip. They are the places where the universe keeps its secrets, waiting for us to find the right questions to ask. Feel the stability of your own world, sustained by a gravity that is gentle and predictable, and contrast it with the extreme geometry of the distant black hole. You are safe in the shallow waters of space-time, far from the steep cliffs of the event horizon. Let the mystery of the threshold remain a distant, quiet hum in the back of your mind. The universe is vast enough to hold both the gentle and the extreme, the known and the hidden. As you drift into a deeper sleep, let the dark, patient majesty of the cosmos cradle you, and find peace in the knowledge that some mysteries are meant to be explored slowly across the span of lifetimes. To understand why gravity and quantum physics must eventually meet, it helps to look not outward into the depths of space, but backward through the long corridors of time. Far beyond the reaches of swirling galaxies and the silent dark anchors of black holes lies an earlier chapter of the universe's story, one so distant and so dense, that it can only be approached through the careful assembly of indirect evidence. This is the story of the beginning, a moment when everything that now exists, every star, every planet, and every atom in your body, was once packed into a state that was unimaginably hot, dense, and small. In those earliest moments of the universe, the concept of scale, which usually protects our understanding, completely collapses in every direction. Distances shrink towards zero, energies rise to levels that defy our everyday logic, and time itself begins to behave in ways that have no modern analogue. The familiar separation between the very large and the very small, the buffer that allows us to use two different sets of rules today, simply disappears. It does not vanish because our theories fail, but because the universe itself no longer provides the room for gravity and quantum effects to remain apart. At the very start of the cosmic clock, gravity could not afford to be the gentle background whisper it is today. With so much mass and energy compressed into such a tiny microscopic region, the curvature of space and time must have been extreme, sharp, and overwhelming. At the same time, because the entire observable universe was smaller than a single atom, quantum effects were not just present, they were the primary rules of engagement. There was no quiet background stage and no stable, unmoving floor. Everything happened at once, everywhere, under conditions that demanded both the smooth language of gravity and the flickering, jumpy language of quantum physics simultaneously. This makes the early universe the most important testing ground for our understanding of reality at its deepest level. Unlike black holes, which are rare and scattered throughout the modern sky, the early universe was a universal experience. Every region of space passed through this intense, unified phase. Whatever rules governed those first few instants helped shape the patterns and structures that would eventually grow into the cosmos we see tonight. Modern cosmology does a remarkable job of describing the history of the universe after those first few frantic moments. We have built a story that explains how space expanded, how matter cooled, how the first light broke through the darkness, and how galaxies eventually emerged from the cooling mist. Our observations of distant light, known as the cosmic microwave background, align beautifully with these models, showing us a snapshot of the universe when it was only a few 100,000 years old. From a split second onward, the story unfolds with an impressive clarity that gives us confidence in our understanding of physics. But when our attention is pushed even closer to the beginning itself, closer to the very first tick of the clock, the picture begins to blur into a conceptual fog. Our current models of the Big Bang rely on gravity being described in smooth classical terms. They assume that space and time behaved as continuous, predictable structures even at the earliest times. This assumption works well for much of cosmic history, but as we wind the clock back further, it becomes increasingly strained. As we approach the moment of origin, distances shrink to scales where quantum fluctuations should have been strong enough to warp the very fabric of space. Energies rise to levels where the restless nature of the small would have been impossible to ignore. At some point, math just stops being trustworthy. It is not necessarily that the equations explode with a sudden dramatic violence, but rather that the assumptions underneath them quietly lose their footing on the reality they are trying to describe. The equations still exist on the page, but their connection to the physical world becomes uncertain, like a compass S, pinning wildly near a magnetic pole. This does not mean the early universe was a place of lawless chaos, or that it is entirely unknowable. It simply means that the tools we currently possess were designed for a world that had already settled into a form where gravity and quantum effects could remain mostly separate. Before that settling occurred, something else was at work. a deeper set of rules that we are still trying to hear through the fading echoes of the beginning. What exactly happened in those earliest moments remains one of the most delicate and profound questions in all of science. It sits at the intersection of two incomplete descriptions of the world. Gravity wants to describe the evolution of space-time as a whole, focusing on the grand expansion and the shaping of the void. Quantum physics wants to describe the fluctuations, the probabilities, and the discrete interactions of the energy within that void. In the early universe, both of these demands are unavoidable and happening in the same tiny space. This creates a limit to our sight, a horizon beyond which our current descriptions lose their sharpness and clarity. Just as a telescope has a limit to how much light it can gather from a distance, our theories have limits beyond which their assumptions no longer hold true. There is something quietly humbling about this realization. The universe in its infancy does not reveal itself easily to us. It leaves behind traces, patterns, and faint echoes in the distribution of matter, but it does not leave a complete, high-resolution record of its birth. This distance in time adds to the sense of mystery. The early universe is not something that happened somewhere else in a distant part of space. It happened right here, everywhere, in the very space you are occupying tonight. Yet, it remains profoundly and fundamentally unfamiliar. The laws that govern your everyday experience, the steady weight of gravity and the reliable structure of matter, had not yet settled into their current comfortable forms. Space and time themselves may have behaved as quantum entities, flickering and jumping in a way that we can barely imagine. Speculation inevitably enters this territory, but it is a careful and restrained kind of speculation. Physicists look for patterns in the modern sky that might have been imprinted by these quantum gravitational events. They ask what sort of behavior could have smoothed the transition from a quantum-dominated beginning to the gravity-dominated expansion we see today. They examine how tiny, microscopic fluctuations in the first moments might have grown into the vast structures of the galaxies we observe with our modern telescopes. What they avoid is the temptation to pretend to know more than the evidence allows. This restraint is part of what makes the problem so compelling and so honest. The early universe is not a failure of our ability to explain things. It is a reminder that every explanation has a scope and a limit. Beyond that scope lies the realm of patient inquiry and careful inference. There is also a sense that the early universe holds the answers to some of our most basic questions: why space appears so smooth on large scales, why time flows only in one direction, and why the fundamental constants of nature fall within the narrow ranges that allow life to exist. These are not questions that can be answered fully without understanding those first moments where gravity and the quantum were one. Yet the universe does not rush us toward these answers. It allows the mystery to remain gentle and distant, a soft light on the furthest horizon of our knowledge. Tonight, as you drift towards sleep, you can think of the early universe not as a violent explosion, but as a quiet, intense beginning whose details are softly veiled by time. It is a place where our familiar concepts blur, not into chaos, but into something much subtler and deeper than we can yet describe. The early universe reflects the challenge of our entire journey. It is a place where we see the need for a unified theory, but lack the eyes to see it clearly. It reminds us that understanding arrives in layers, and that we are still uncovering the most foundational layer of all. Feel the immense age of the space around you. Let the fading echoes of the beginning bring a sense of perspective to your thoughts. You are a part of a story that has been unfolding for nearly 14 billion years, a story that began in a moment of perfect unified mystery. Let the vastness of that history and the silence of the origins guide you into a deep and restful state, knowing that the universe is patient with its secrets, and that you are a vital part of its long unfolding dream. In the quiet intersection where quantum mechanics meets the heavy, unyielding curvature of gravity, there lies a puzzle that does not concern matter or force, but something much more abstract and fundamental: information. To understand why gravity and the quantum world are at odds, we must consider the idea that the universe is not just made of atoms and energy, but of data. In the realm of the small, quantum physics treats information as a sacred and indestructible thing. Every particle has a story, a set of properties like its position, its spin, and its velocity that define exactly what it is. According to the deep laws of the quantum, this information can never be truly erased from the cosmic ledger. You can burn a book, turning its pages into ash and smoke, but in the eyes of a quantum physicist, the information is still there, scattered into the vibrations of the air and the arrangement of the soot. If you had a powerful enough computer and K knew the exact state of every atom, you could, in principle, reconstruct the book. The universe, at its most basic level, is an archivist that never loses a single file. However, when we introduce the extreme gravity of a black hole into this picture, the archivist faces a paradox that threatens the very foundation of how we define reality. For a long time, the traditional view of gravity suggested that once something falls into a black hole, it is effectively removed from our universe. The black hole was seen as a one-way door, a place where matter and the information it carries are crushed into a single point of infinite density. From the outside, the black hole seems to have no memory of what it has consumed, whether it swallowed a library of philosophy or a massive star. The only things it reveals to the rest of the world are its mass, its spin, and its charge. This baldness of black holes suggests a profound loss of detail. If the black hole were to exist forever, the information might simply be hidden away, tucked behind the event horizon like a secret kept in a locked room. While frustrating for us, it would not necessarily break the laws of quantum physics, as the information would still exist somewhere, even if we could never reach it. But the mystery deepened when we realized that black holes are not eternal. As we explored in previous chapters, quantum fluctuations near the event horizon cause black holes to slowly leak energy in the form of radiation. Over unimaginably long spans of time, a black hole will lose its mass, shrink, and eventually vanish entirely in a final puff of energy. This leads us to the heart of the information paradox. If the black hole disappears, and the radiation it emitted was purely random and thermal, what happens to the information that was once trapped inside? If it is gone, then a fundamental law of quantum mechanics has been broken. The cosmic ledger has been torn, and the universe has forgotten part of its own history. This is not just a technicality, it is a crisis. If information can be destroyed, then the predictability of physics, the idea that the past determines the future, begins to crumble. It would mean that the universe is not a cohesive story, but a collection of fragments that can be deleted without a trace. This clash over the fate of information is one of the most significant battlegrounds in the attempt to unify gravity and quantum physics. It forces us to ask what space and time are actually made of. Some physicists have begun to propose that information might not be stored in the volume of space, but rather on its surfaces. This is a concept known as the holographic principle. To understand this, imagine a soda can. The liquid inside the can has a volume, but all the information about what is in the can, the ingredients, the brand, the nutritional facts, is written on the label on the surface. In a similar way, it has been suggested that all the information about the objects that fall into a black hole might be smeared across its event horizon, encoded in the subtle ripples of the boundary. When the black hole evaporates, the radiation might carry that information back out into the universe, preserving the quantum ledger. If this is true, it suggests that our three-dimensional world might be a kind of projection from a two-dimensional surface, a realization that would change our entire understanding of the geometry of the immense. The mystery of information also forces us to reconsider the nature of entanglement, the strange quantum connection that allows two particles to remain linked across vast distances. Some of the most recent and daring ideas in physics suggest that this quantum spookiness might be the very thing that stitches space-time together. In this view, space is not a hollow container, but a manifestation of information exchange. If you were to break the entanglement between particles, the space between them might simply cease to exist. This would mean that gravity, which is the shape of space, is actually a result of how information is organized at the smallest scales. The whisper of gravity and the restless world of the quantum would finally be revealed as two sides of the same coin, one describing the data and the other describing the medium on which it is written. As we dwell on the mystery of information, we begin to see that the struggle to explain gravity is not just about measuring forces, but about understanding the very fabric of knowledge. The universe is a vast, interconnected network of events, and gravity is the way that network holds its shape. The fact that we find it so difficult to reconcile these ideas is a sign that we are standing on the edge of a new way of thinking. We are moving away from a world of solid objects and toward a world of relationships and encoded truths. The information paradox is a guide, pushing us to look past the surface of things and into the deep logic that governs the beginning and the end of all things. It reminds us that even when things seem lost in the dark, the universe retains a memory of everything it has ever been. Tonight, as you drift toward a deeper rest, let the idea of this indestructible cosmic memory bring you a sense of security. Every thought you have had, every breath you have taken, and every moment you have experienced is part of the grand, unfailing archive of the universe. You are not a fleeting shadow. You are a vital piece of information in a story that never loses its place. Feel the weight of the gravity that connects you to the Earth, and the silent quantum links that connect you to the stars. The world is more than what we see. It is an elegant tapestry of data, woven with care, and preserved with a relentless, quiet fidelity. Let the complexity of these ideas soften into a gentle hum. You do not need to hold all the data in your mind to be a part of the harmony. The universe remembers you. Let go of the need to know and trust in the silence of the night, where the mystery of information resides in perfect, undisturbed peace. The ledger is safe, the story is whole, and you are resting exactly where you belong in the grand architecture of the mall. For most of the history of modern physics, there has been an assumption that sits quietly and comfortably in the background of every major discovery. Gravity is treated as one of the four fundamental forces, a basic building block of reality that sits alongside the forces governing electricity, magnetism, and the tiny, powerful cores of atoms. It is seen as something that was present at the very first moment of the universe, a primary actor on the cosmic stage that should, in principle, have a direct quantum description just like everything else. But as the effort to unify gravity with the quantum world has stretched on for decades without a final resolution, an intriguing and slightly radical question has become much harder to avoid. What if gravity is not quite the same as other forces? What if our struggle to reconcile the two is not merely a technical difficulty with our mathematics, but a deep conceptual error in how we view the nature of space and time? What if gravity is not waiting to be quantized in the usual way because it is not a conventional fundamental force at all, but rather something that emerges from a deeper hidden layer of reality? This idea is controversial among many scientists for a very simple and understandable reason. Quantum physics has been so astonishingly successful at describing the interactions of the universe in terms of quantum phi, LDS, and the exchange of discrete particles. It has explained the vast majority of nature by treating forces as arising from underlying quantum behavior. In that context, it feels only natural to assume that gravity should eventually fit into that same elegant pattern. If everything else can be described quantum mechanically, we wonder, why would gravity be exempt? And yet, gravity has always maintained a strange and unique status in our equations. As we have explored, it does not simply act within space and time like a guest in a house. It is the very shape of the house itself. This distinction sounds like simple wordplay until it is taken seriously. If gravity is the structure of space and time, then treating it like a force traveling through a fixed background may be entirely the wrong starting point. Perhaps gravity is not another actor on the stage, but rather part of what makes the stage exist in the first place, an emergent property of something even more fundamental. One speculative but fascinating possibility that has gained traction in recent years is that gravity might be emergent, meaning it arises from deeper processes rather than existing as a basic fundamental interaction on its own. To grasp this intuitive picture, we can look at other phenomena in our world that look fundamental from one scale but are actually the result of many smaller parts working together. Temperature, for example, feels like a basic and essential property of a substance. We can feel the heat of a cup of tea, or the cold of an ice cube quite clearly, yet, if we zoom into the level of individual molecules, the concept of temperature disappears. There is no such thing as a hot molecule or a cold molecule. Instead, there are only molecules moving at different speeds. Temperature is an emergent property. It is what we perceive when we average out the collective motion of ons of tiny particles. In this view, gravity might be more like temperature than like a fundamental force. It could arise from the collective behavior of microscopic ingredients of reality that are not themselves gravitational in any sense we would recognize. Space and time might have their own underlying building blocks, and gravity might be the large-scale behavior that results when those building blocks interact and organize themselves. This perspective is intriguing because it would naturally explain why gravity feels so smooth and continuous to our senses. If gravity is an emergent, averaged effect, then its continuity would be a natural consequence of having many billions of small, discrete contributions blending together into a single, unified flow. It could also explain why our attempts to quantize gravity directly have been so frustratingly difficult for the last century. If gravity is not fundamental, then trying to treat it as a quantum force might be like trying to find the quantum of temperature. One can study the individual molecules that cause heat, and those molecules certainly follow quantum laws, but temperature itself is not a fundamental quantum object. It is a macroscopic description of a system in bulk. Perhaps gravity belongs in a similar category, a beautiful high-level summary of a much more complex and hidden quantum story. Another speculative thread in this emergent perspective asks whether space and time themselves may not be the bedrock of reality. Quantum physics typically assumes a background of space and time as a given, a container in which all events occur. Gravity, through general relativity, suggests that this container is dynamic and responsive. Unifying the two may require a picture where space and time are not the starting points, but rather the end results. Some theories suggest that space-time is woven together by quantum entanglement, that strange connection that links particles across any distance. If this is true, then the geometry of the universe is actually a map of how information is shared between its most basic parts. Suggesting that space and time are emergent can feel like suggesting that the floor beneath your feet is optional, but physics has repeatedly found that what feels most basic is not always most fundamental. Solid surfaces, after all, are mostly empty space when viewed at the atomic level, and continuous motion becomes discrete energy levels when we look closely enough. Still, the controversy remains, and many physicists believe that gravity must have a direct quantum description, even if it is currently hidden from us by our lack of a proper mathematical language. They point out that every other force once seemed mysterious until the right framework was found, and they argue that gravity couples to energy, and since quantum systems carry energy, gravity must, in some sense, be quantized. In their view, gravity is simply the last force waiting for its proper quantum dialect. This is a reasonable and disciplined expectation, and it remains the dominant path of research today. It keeps the search focused and grounded in the methods that have served science so well for centuries. But the alternative, emergent perspective persists because it addresses something more philosophical and physical. It asks whether our desire for a single unified description at all scales is a requirement of nature or a preference of the human mind. The uncertainty here is gentle and open-ended. There is no need for us to declare today that gravity is non-quantum, or to insist that it must be one way or the other. The honest position, and the one that allows for the most growth, is that the universe has not yet made its final answer visible to us. What we can say with certainty is that gravity behaves unlike any other force we have ever studied. It shapes the very background of our lives rather than acting within it. It remains smooth where everything else is granular. That resistance might be a clue that gravity is special, or a clue that our categories are still too small to hold the truth. In the history of science, progress often begins when someone asks a question that feels slightly uncomfortable, not because it is dramatic, but because it forces us to reassess what we have taken for granted for a long time. The question of whether gravity is an emergent illusion is one of those powerful questions. Tonight, As you drift toward sleep, let the idea of emergence bring a sense of wonder to your rest. Imagine the world not as a collection of hard fixed objects, but as a deep and layered symphony where the most solid things, the ground, the air, and even the passage of time, are the result of a much more intricate and beautiful hidden order. You are a part of that emergence, a complex and conscious being arising from the simple interactions of atoms. Feel the steady pull of gravity holding you, and consider that it might be the universe's way of summarizing a vast and invisible quantum connection. There is no need for certainty tonight. It is enough to inhabit the mystery and to trust in the layers of the world. Let the boundaries of what you think you know soften into the dark. The universe is in no hurry to reveal its foundations, and you can rest safely in the knowledge that even the most fundamental things are part of a story that is still being told, one layer at a time. At some point in every deep scientific question, it becomes useful to pause and ask what is actually being sought when we try to bridge the gap between gravity and the quantum world. When physicists say they want to explain the universe, they are often navigating the complex boundary where mathematics meets the limits of human intuition. Science is exceptionally good at prediction, but prediction and understanding are not always the same thing. Given the right conditions, our equations can tell us how systems will behave with an accuracy that borders on the miraculous. We can forecast the movement of planets across centuries, the behavior of atoms within a silicon chip, and the bending of light around a distant star. These are not vague guesses, they are precise, repeatable, and breathtakingly reliable. And yet, the desire to unify these two great pillars of physics persists because our minds crave a story that is not only accurate but also intuitive. We seek a conceptual unity that matches our internal sense of how a single universe should function. Part of this struggle stems from the fact that our brains evolved to survive in a very specific environment, the middle scales of reality. For millions of years, our ancestors did not need to understand the curvature of space-time or the probabilistic nature of electrons to find food or avoid predators. Our intuition was shaped by the behavior of solid objects, the steady flow of time, and the reliable pull of the Earth. We are biologically tuned to a world that is classical, local, and certain. Because of this, when we zoom into the quantum level or out to the cosmic scale, we find that the universe behaves in ways that our instincts find deeply offensive. We want things to have a definite position. Quantum physics says they are clouds of possibility. We want time to be a universal constant. Gravity says it is a local and flexible experience. The tension between gravity and quantum mechanics is, in many ways, the ultimate expression of the limits of our own biological perspective. We often mistake our inability to visualize a concept for a failure of the theory itself. When we encounter the idea that space can curve or that a particle can be in two places at once, we feel a sense of intellectual friction. This discomfort is not necessarily a sign that the science is wrong, but that we are reaching the edge of what our evolved senses were designed to process. Throughout the history of science, we have seen that nature does not promise simplicity or visual clarity. It does not promise that every successful description must emerge from a single, easy-to-visualize framework. Sometimes, different levels of description coexist because they address different questions at different scales. A weather forecast does not require a molecular description of every air particle to be useful, and a map of a mountain range does not need to show every grain of sand to be accurate. In this light, the coexistence of gravity and quantum physics could be seen not as a failure of logic, but as a reflection of the layered complexity of the universe, a complexity that simply exceeds the reach of human intuition. This raises a subtle and important question. When we ask for a theory of quantum gravity, are we seeking better predictions or a more satisfying story about reality? In many cases, the predictions we have already work perfectly. The lack of unification does not prevent our modern technology from functioning or our observations from being made. Satellites remain in their precise orbits, and atoms in our laboratories behave exactly as calculated. What feels missing is not predictive power, but conceptual coherence. We want the universe to be a single, seamless narrative, and the fact that it currently requires two incompatible sets of rules feels personally unsatisfying. This desire for unity is a powerful motivator for inquiry, but it is also a human preference. The universe may not be under any obligation to provide us with a single unified equation that fits on a t-shirt. It may be that reality is fundamentally pluralistic, requiring different languages for different depths of experience. The layered approach to science has been extremely successful, but not everything yields easily to this kind of reduction. Often to explain something means to show how it arises from simpler pieces. We say atoms explain chemistry, and chemistry explains biology. But as we have seen with the concept of emergence, some patterns only appear when many pieces work together. Temperature and pressure are real and useful, but they are not fundamental properties of a single particle. Gravity might occupy a similar position. It might be a macroscopic description that only makes sense at a certain scale, much like the image on a screen only becomes clear when you step back from the individual pixels. If this is true, our attempt to quantize gravity might be a category error, an attempt to apply the rules of the pixels to the image itself. Our intuition tells us that the small must build the large, but the large may possess qualities that the small simply cannot contain. There is also a human element to this quest for an explanation that is easy to overlook. Explanations are not only about nature, they are about how our minds make sense of what we observe. A good explanation feels satisfying, it reduces our sense of surprise, and creates a feeling of aha, even when the underlying complexity remains. This psychological satisfaction is what drives us to keep digging, to keep asking why the smooth fabric of gravity resists the grainy texture of the quantum. But we must be careful not to let our desire for a neat ending tempt us into demanding answers before the evidence is ready. A slower, more patient approach accepts that explanation sometimes unfolds gradually, across generations. It acknowledges that different layers of description can coexist for long periods of time, and that our understanding can deepen without necessarily converging into a single point right away. This slower view invites us to linger in the mystery. Rather than asking how we can force gravity into a quantum box, we can ask what it would truly mean for us to succeed. Would success be a single framework where both theories emerge naturally? Would it be a new set of predictions we haven't yet imagined? Or would it be a profound conceptual shift that changes how we think about space, time, and matter entirely? It is possible that the final explanation will look very different from anything we can currently visualize. It may require us to let go of assumptions that feel deeply ingrained in our very being. It may require us to admit that our intuition is not the ultimate judge of truth. In the history of physics, we have often had to trade our common sense for a deeper accuracy, and the problem of gravity and quantum mechanics may be the greatest trade we have ever been asked to make. As the night continues and the world around you stays still, you can find a quiet comfort in the limits of your own intuition. You do not need to be able to visualize the curvature of space or the probability of an atom to be a part of the universe. You are a biological being, perfectly adapted for the world of the middle scales, resting in a reality that is far more vast and intricate than your senses were ever meant to perceive. The fact that we can even ask these questions is a testament to our curiosity, but our inability to answer them immediately is a testament to the depth of the world. Let the friction of these ideas soften. You do not need to solve physics paradoxes to find rest. The universe is functioning perfectly well without our complete understanding. Trust in the layers of reality that support you, from the atoms vibrating in your cells to the gravity holding you to the earth. Let the need for a final, unified story fade away into the quiet of the night, and find peace in the knowledge that some mysteries are meant to be lived with, rather than solved. The search for a deeper understanding of gravity did not begin because something in the physical world was obviously broken or malfunctioning. It began because something in our collective description of that world was quietly, persistently unfinished. Once physicists realized that the universe was being described by two incredibly powerful but fundamentally incompatible frameworks, the question of unification became unavoidable. If both descriptions are true in their own respective domains, then something more fundamental, more basic, must sit beneath them, waiting to be recognized. This realization has been guiding research for decades, not as a single project with a clear end point or a simple deadline, but as a long, patient effort to understand what gravity really is when it is examined at the smallest meaningful scales. The goal is not to discard what already works, for quantum physics and general relativity are two of the greatest triumphs of the human mind, but to discover a framework that explains why those successful ideas exist in the first place. What makes this problem feel so foundational is that gravity is not just another interaction among many, it is the architect of space and time themselves. Any attempt to unify it with the quantum world, therefore, touches the deepest assumptions we have about how reality is structured. Questions about gravity quickly become questions about the very nature of existence. How does space emerge? What is the flow of time? And what does it mean for something to occupy a position in the void? Because of this, the search for quantum gravity is not driven by a single experimental anomaly or a practical need to fix a machine. It is driven by the desire for consistency. Physics aims to tell a coherent and unified story about the universe, one that does not rely on shifting rulebooks depending on the scale of the object in question. As long as gravity and quantum physics remain disconnected, that story feels like a book with its middle chapters missing. This sense of incompleteness is not a burden, it is a gift that has motivated generations of thinkers to look past the obvious and into the hidden. Some have approached this unfinished business mathematically, exploring how the language of quantum theory might be reshaped or expanded to accommodate the curvature of space. Others have started from gravity itself, asking how its geometric description might change or pixelate when examined closely enough. Still others have questioned the very assumptions that both theories share, wondering whether space and time themselves might not be fundamental building blocks at all, but rather side effects of a deeper quantum entanglement. What unites these diverse efforts is not a shared method or a single school of thought, but an immense and necessary patience. Progress in this area of science has been slow and often indirect. There have been promising ideas that led to dead ends, partial successes that revealed even deeper puzzles, and occasional false starts that required years of revision. None of this is unusual in the history of deep inquiry. Foundational problems rarely yield to quick solutions, especially when they involve rethinking concepts that have worked remarkably well for over a century. It is also important to recognize what this search is not. It is not a competition to replace existing theories or to prove one side wrong. Quantum physics and general relativity are not rivals fighting for dominance in a zero-sum game. Each continues to do its job extraordinarily well in the modern world. The goal is not to declare a winner, but to understand how both fit into a larger, more comprehensive picture. In many ways, the effort resembles the careful exploration of an unknown continent rather than the construction of a new building. Physicists probe the edges of known theories, looking for hints of a deeper structure. They examine where the calculations fail, where the assumptions clash, and where new ideas might naturally sprout from the tension. The process is less about bold declarations of truth and more about listening closely to what the mathematics and the observations are quietly suggesting in the dark. Because the problem is so deep and the stakes are so high, researchers have learned to be cautious about their claims. Grand unifying ideas are tempting, but nature has shown little interest in accommodating human shortcuts. Any successful description of quantum gravity must be able to reduce down to quantum physics where gravity is weak, and to the current theory of gravity where quantum effects are negligible. It must respect everything that is already known while simultaneously extending our understanding into entirely unfamiliar territory. This requirement alone imposes a remarkable level of discipline on the scientific community. It ensures that new ideas remain grounded and tethered to reality even when they venture far from our familiar human intuition. It also explains why progress can feel gradual rather than dramatic. Each new step must fit seamlessly into a vast, existing structure of knowledge that has been built over hundreds of years. There is also a significant cultural aspect to this long search. The problem of the unfinished theory has encouraged collaboration across fields that once felt distant and disconnected. Particle physicists, cosmologists, mathematicians, and even philosophers have found themselves asking the same overlapping questions. What is the fabric of space made of? How does the arrow of time emerge from a world that seems reversible at the microscopic level? Are there fundamental limits to what can be measured or known? These are not questions confined to a single laboratory or discipline. Despite the abstract and often difficult nature of the work, there is a quiet optimism that runs through the community. It is not the optimism of expecting a final solution tomorrow morning, but the steady optimism of believing that the universe is intelligible, that the patterns we observe are not arbitrary accidents, but part of a deeper order that is waiting to be uncovered by the curious, gentle humor occasionally surfaces in how physicists talk about the problem. There is an awareness that trying to unify gravity and quantum physics can feel like persuading two incredibly stubborn languages to share a single grammar. Each speaks fluently and beautifully on its own, yet both resist a direct and easy translation. The task is not to shout louder or to force the translation through sheer willpower, but to learn how to listen to the universe in a different way. This long view helps explain why the search has continued even in the absence of direct experimental confirmation. Some of the scales involved are so extreme that building the necessary experiments may take many generations, or may never be fully possible within the limits of our technology. Rather than discouraging the inquiry, this limitation has sharpened it, forcing ideas to be internally consistent, mathematically robust, and conceptually clear before they are even shared. The search for quantum gravity is therefore as much about refining our own understanding as it is about making a new discovery. Even approaches that ultimately turn out to be incomplete or incorrect can illuminate hidden assumptions or reveal unexpected connections between seemingly different parts of nature. In this way, progress is not measured solely by the answers we find, but by the quality and the depth of the questions that arise along the way. There is a sense of continuity with the past here. Physics has faced similar moments before when existing theories worked perfectly within their domains but failed to align with each other. Each time, the resolution required a fundamental shift in perspective rather than a simple correction or a minor adjustment. Remembering this history encourages a unique kind of patience. It suggests that the confusion we feel now is often the necessary prelude to a new kind of clarity. What makes our current situation distinctive is just how successful the existing, separate theories are. Quantum physics and gravity are not rough approximations waiting to be discarded. They are precise, reliable, and deeply trusted pillars of our world. Any unifying framework must therefore be subtle enough to preserve their individual successes while explaining their differences. This is why the search feels less like chasing a missing piece of a puzzle and more like uncovering a hidden, foundational layer of a building. Gravity may not simply be another force waiting to be quantized. Quantum physics may not simply need a small adjustment. Both may be reflections of a reality we have yet to fully recognize. Seen this way, the problem becomes less frustrating and more intriguing. The refusal of the theories to merge easily suggests that the universe is guarding a deeper secret, one that requires creativity and humility to approach. Rather than racing toward a conclusion, we can appreciate the journey itself. The search for quantum gravity unfolds slowly, shaped by curiosity rather than urgency. It is driven by a desire to understand, not conquer or finish. In that sense, the effort mirrors the very universe it seeks to describe, vast, intricate, and finitely patient. It is a reminder that some of life's most important questions are not meant to be answered quickly. They are meant to be lived with, explored, and gradually illuminated over a long span of time. When theories refuse to cooperate, it is tempting to see the situation as a dead end or a wall that we cannot climb. But in the long history of science, such moments often mark the true edge of human understanding rather than its failure. They indicate that the language being used has reached its natural limits, and that the silence following our unanswered questions is not empty, but heavy with hidden potential. Gravity and quantum physics do not argue loudly with each other, they simply talk past each other, like two people speaking different languages in a quiet room. And in that quiet disagreement lies one of the deepest clues we have about the structure of reality. Learning to listen to this silence requires a shift in how we think about progress. We are used to progress being a loud announcement, a breakthrough, or a new discovery that fills the headlines. But sometimes progress is found in the steady, patient observation of what remains unsaid. It is found in the gaps where our current logic fails to hold weight. Studying gravity at quantum scales turns out to be difficult for a reason that is both simple and deeply inconvenient for our modern instruments. Gravity is extraordinarily weak, and quantum effects only reveal themselves clearly when systems are extraordinarily small. Bringing those two conditions together requires circumstances that sit far beyond anything normally accessible to us on this planet. In our everyday experiments, gravity is easy to observe because we deal with large masses like the Earth and the Moon. Drop an object, and it falls with a predictable rhythm. But these effects emerge from the combined influence of enormous numbers of particles acting together in a single direction. At the level of individual particles, gravity is so faint that it is completely overshadowed by the electromagnetic and nuclear forces. Quantum experiments, by contrast, thrive on isolation and extreme delicacy. They are designed to study tiny systems in carefully controlled conditions, often shielded from any outside influence. In this quiet, sheltered environment, quantum behavior becomes visible, but gravity almost entirely disappears from our view. Trying to observe the quantum aspects of gravity therefore demands a strange and difficult combination. One needs systems that are both extremely small and enormously massive, or situations where space and time themselves are distorted at tiny scales. Nature does provide such environments, but they are not conveniently located for our inspection. As we have explored, black holes and the very early universe are the two primary places where these conditions are met. Yet black holes are distant, hostile, and not inclined to cooperate with our measurements. They do not sit patiently in our experimental chambers. They reveal themselves only indirectly through their influence on surrounding matter and light. The early universe is equally elusive, having occurred billions of years ago. While we can see its traces in the cosmic microwave background, we cannot recreate its conditions directly. This is where the challenge of science becomes a challenge of technology and patience, rather than just imagination. Physicists can describe the kinds of experiments that would be ideal to settle these questions, but they cannot yet build the machines required to carry them out. To probe quantum gravity directly would require energies far beyond what any current particle accelerator can reach. The gap between what we can measure and what we need to measure is not a small step. It is a mat of many orders of magnitude. This gap can be frustrating, but it is also revealing. It reminds us that physics does not advance only through clever ideas, but through the slow development of tools, materials, and engineering. Imagination can move much faster than instrumentation, and in the case of gravity, it has done exactly that. But the absence of direct experimental confirmation does not mean work has stalled. We have learned a great deal by studying indirect effects, consistency requirements, and the rigid mathematical constraints that any new theory must follow. A proposed idea about quantum gravity must agree with everything we already know to be true. It must not contradict the well-tested results of quantum mechanics or the proven geometry of general relativity. These constraints are incredibly powerful without new data. They act as a filter, allowing only the most robust and logically sound ideas to survive. There is also immense value in simply understanding why experiments are so difficult. The fact that gravity is so weak at small scales explains why our world is so stable. If gravity was strong at the level of the atom, the delicate balance of chemistry and biology might be impossible. Matter would be unstable, and the structures of life might never have formed. The difficulty of measurement is itself a clue about how the universe is organized. It suggests that nature has provided a quiet separation between the rules of the small and the rules of the large to allow for a complex and habitable reality. This perspective helps soften the frustration of our current limits. The lack of experimental access is not a sign that something has gone wrong in our scientific journey. It is a reflection of how nature has arranged itself for our benefit. Gravity and quantum effects occupy different ranges of scale so effectively that forcing them together requires extraordinary circumstances that the universe rarely demands. Over time, our technology will continue to advance. Detectors will become more sensitive, and our observations of the cosmos will become even more precise. We have seen this happen before. Gravitational waves, for example, were predicted by Einstein long before we had the technology to hear them. Their eventual detection required decades of refinement and the construction of instruments capable of measuring a change in distance smaller than the width of an atom. This history offers a useful and comforting reminder as we look toward the future. The absence of evidence today does not mean evidence will never arrive. It often means that the question is simply ahead of its tools. Physics has encountered this situation many times, and each time progress eventually followed, though rarely on a convenient human schedule. Meanwhile, the search continues through indirect paths. We examine cosmic signals from the edge of the visible universe, look for subtle deviations in the orbits of distant stars, and test the theoretical consistency of our latest models. There is a quiet discipline in this approach. Rather than declaring defeat or rushing to a conclusion that cannot be supported, researchers refine their questions and allow the uncertainty to remain open. This patience is not the same as resignation. It is a recognition that true understanding sometimes requires as much waiting as it does working. Quantum gravity, if it reveals itself to us experimentally, is unlikely to do so with a dramatic flourish. There may be no single eureka moment that settles everything at once. Instead, evidence may accumulate slowly through small hints that align over time, a pattern of whispers rather than a single proclamation. Until then, the silence we encounter when we ask about the quantum nature of gravity should be respected. It is a reflection of the scale of the problem and the ambition of our inquiry. Few areas of science attempt to probe such extreme conditions or such fundamental aspects of reality. In this light, the difficulty of experimentation becomes an essential part of the story rather than an obstacle to it. It highlights how far our understanding has already come and how carefully the universe guards its deepest workings. Gravity at quantum scales remains elusive, not because it is unreachable in principle, but because it lives at the far edges of what we can currently touch and test. And in the world of physics, those edges have a long and successful history of slowly, patiently moving outward. As you rest tonight, allow your mind to move away from needing immediate answers. Feel the vast, quiet space of the unknown and realize that it is not a void, but a frontier. The universe is in no hurry to be understood. There is a profound peace in listening to the silence of a mystery that is still waiting to be solved. Trust in the steady progress of time and the enduring power of human curiosity, and let yourself be carried into sleep by the quiet, gravitational pull of a world that is still full of wonderful, unanswered questions. Science is often imagined as a steady, inevitable march toward absolute certainty, a sequence of questions answered, mysteries resolved, and gaps neatly closed. From a distance, that story can seem incredibly reassuring, suggesting a final destination where understanding is complete, and the universe finally makes sense in a finished, polished way. But live science rarely feels like that. As we reach the horizon of what we currently know about gravity and the quantum world, we find that the picture is much more nuanced. Most of the time, science moves forward while carrying uncertainty alongside it, like a traveler moving through a fog with a lantern. T only illuminates the next few steps. Explanations work well enough to be trusted, yet they leave edges unexplored. Models predict outcomes with staggering accuracy, yet they rest on assumptions that are known to be incomplete. Progress in our understanding of the cosmos does not wait for perfection, it proceeds with what is available, refining our view of reality one layer at a time. Living with an incomplete picture of the universe requires a particular kind of intellectual humility. It means accepting that our knowledge can be reliable and transformative without being final or ultimate. It means recognizing that our explanations can be useful for building civilizations and exploring the stars without being the absolute last word on truth. Gravity and quantum physics offer the clearest possible example of this modest posture. Both theories are trusted by the brightest minds of our age. Both are tested daily in the most rigorous environments we can create. Both are used daily to make predictions that allow our global infrastructure to function. And yet, we know they do not fit together cleanly. Rather than forcing a premature or hollow resolution, science has learned to work carefully within this tension, treating the mismatch not as a failure, but as a boundary that defines the current horizon of human knowledge. This way of working can feel unfamiliar or even frustrating outside the world of science. In many areas of our lives, uncertainty is treated as a problem to be eliminated as quickly as possible. Decisions are expected, clear answers are preferred, and ambiguity can often feel like a source of discomfort or anxiety. Science, by contrast, has learned to tolerate ambiguity for incredibly long periods of time, sometimes for many generations. This tolerance is not a sign of stagnation, it is a sign of strength, because it creates a necessary space. It allows ID as to mature slowly and naturally. It allows evidence to accumulate from across the globe before conclusions are drawn. It allows mistaken paths to be explored and then discarded without panic, because in the scientific method, retreat and revision are vital parts of the process rather than signs of failure. There is a quiet, steady confidence in this approach. We trust that the universe is consistent even when it is not yet fully understood. We trust that the unanswered questions at the edges of our theories are not signs of chaos, but indicators of a deeper, more profound depth. Certainty and curiosity behave very differently in the human mind. Certainty tends to close conversations and stop the flow of inquiry. Once something is declared finished and solved, attention naturally moves elsewhere. Curiosity, on the other hand, keeps the questions alive and breathing. It invites us to keep revisiting old ideas, to keep re-examining our most basic assumptions, and to listen more carefully to what nature is showing us in the quiet moments. In the history of physics, certainty has almost always been provisional. Concepts that were once thought to be final and complete have later been absorbed into broader, more expansive frameworks. What mattered in those transitions was not that the earlier ideas were wrong, but that they were incomplete. Each stage of our understanding provided a stable platform from which we could see just a little bit further toward the horizon. This layered structure of knowledge is deeply comforting when viewed slowly. It suggests that our understanding of the world does not collapse when a gap appears. Instead, it expands to eventually include that gap. Living with an incomplete picture also encourages a necessary modesty. It reminds us that no single perspective or theory, no matter how successful, captures the entirety of reality. Different Ds. Cryptions can coexist, each illuminating a different aspect of the world, much like different artists might paint the same landscape from different angles. The absence of a single unified story about gravity and quantum mechanics does not imply confusion or a lack of direction. It reflects the immense richness and complexity of the subject matter itself. There is a gentle balance to be found here. Science does not celebrate ignorance, but it does respect the limits of its own reach. It distinguishes between not knowing because something has not been studied yet, and not knowing because the question itself reaches beyond the tools we currently possess. The latter is not a deficiency, it is a frontier, and frontiers are not meant to be crossed immediately through force. They are meant to be approached with care, preparation, and respect. This attitude helps explain why the current lack of a theory of quantum gravity does not generate a sense of alarm in the scientific community. There is no feeling that something urgent or vital has been missed. Instead, there is a calm recognition that some questions unfold on a much slower schedule than we might prefer, revealing their structure only after long periods of quiet preparation. That preparation includes developing new mathematics, inventing new experimental techniques, and learning entirely new ways of thinking about the world. It also includes the difficult work of learning how to sit comfortably with uncertainty without letting it harden into a rigid dogma or dissolve into groundless speculation. Emotionally, this stance can be incredibly settling. It removes the artificial pressure to resolve everything at once and replaces a frantic urgency with a steady, enduring patience. It allows us to appreciate how much we already understand, even as we remain open to what we do not. There is even a quiet joy to be found in this. Incompleteness. It keeps the spirit of discovery alive for future generations. It ensures that wonder does not end the moment an explanation is written down. Each answer we find opens up further questions, not as a burden to be carried, but as a fresh invitation to explore. In the case of the long-standing tension between gravity and the quantum, living with an incomplete picture means accepting that the universe may not yet be ready to give up all its secrets. Or perhaps it means that our collective understanding has not yet learned how to ask the right questions in the right way. Either possibility is perfectly acceptable. Science does not require absolute certainty to function at its highest level. It requires honesty, relentless curiosity, and a deep sense of care. It progresses not by pretending to know more than it does, but by clearly marking exactly where knowledge ends and where inquiry begins. As our journey through the mysteries of gravity and quantum physics nears its later stages, there is no need for a dramatic or forced resolution. The absence of final, absolute answers does not leave a void in our lives. It leaves a landscape that is still open, vibrant, and ready for exploration. That openness can feel deeply peaceful when viewed in the right light. It suggests that understanding is not a task to be completed or a product to be purchased, but a process to participate in, a lifelong conversation with the universe. Living with an incomplete picture does not mean living with confusion. It means living with a heightened awareness of the known and the unknown. In that awareness, curiosity becomes steady and reliable rather than restless. Reflection becomes possible without the sting of disappointment. The universe does not insist on being fully understood all at once. It allows us to peel back its layers gradually, with long, patient pauses in between. And you drift into a deeper rest tonight. You can feel the comfort of that pace. You are a part of a reality that is far larger than any single theory, resting in the safety of a world that is still full of beautiful, open questions. Trust in the horizon of knowing, and let the silence of the night be a gentle reminder that the best parts of the story are often the ones that are still being written. In this final journey tonight, we return to the quiet realization that has carried us through every layer of this mystery, that the universe is in no hurry to be understood. Gravity has been our silent companion throughout this entire exploration, moving quietly in the background of our thoughts, just as it moves in the background of our lives. It has shaped the planets that wander the dark, anchored the galaxies that swirl in the void, and curved the very fabric of space and time. And yet it has remained familiar enough to fade from our daily notice. From the very beginning, our question was never whether gravity works. Its reliability is the bedrock of our physical existence. The true question was why something so steady and so dependable still resists being fully woven into the deepest, most intricate descriptions of our reality. As we settle into these final moments, that question remains open, and we must recognize that this openness is not a failure of our intellect, but a testament to the profound depth of the world we inhabit. Physics has already come remarkably far, uncovering the patterns that allow us to predict the behavior of the cosmos with breathtaking precision. Yet it has also learned the value of a mystery that persists. The story of gravity and the quantum is a reminder that knowledge is not a finish line we are racing toward, but a process of unfolding that occurs on a scale much larger than a single human lifetime. Along the way, we have learned that not every question yields immediately to our demands for clarity. Some mysteries remain because they are foundational, sitting at the very base of what it means for space and time to exist. Gravity sits among these, familiar enough for us to trust with every step we take, yet subtle enough to resist the final definitive explanation we crave. There is a quiet beauty in that balance. Not knowing everything does not diminish what we have already earned. Instead, it gives our knowledge a necessary context. It reminds us that our understanding grows outward from what is solid and proven, rather than inward from what is missing. The unanswered questions do not erase the triumphs of the past, they rest beside them, expanding the landscape of our curiosity rather than breaking the continuity of our science. Gravity remains a constant part of your everyday life, even as these deep questions remain unresolved. It is present in the weight of a cup resting on your bedside table, in the slow and graceful arc of a falling leaf, and in the quiet pull that keeps your feet grounded and the oceans held close to the heart of the planet. It does not demand your attention, and it does not announce its complexity with a loud voice. It simply continues to function with a relentless and peaceful fidelity. Perhaps this is the most appropriate way for the universe to behave. It does not seem built for complete and sudden disclosure, but rather for a gradual revealing that allows our understanding to deepen while leaving ample space for wonder. Gravity, in its polite refusal to fully explain its quantum nature to us just yet, becomes a reminder of that cosmic pace. It is a reminder that we are part of a story that has been unfolding for billions of years and will continue to unfold long after we have found our rest. The question of why quantum physics cannot yet explain gravity remains an invitatio, rather than a wall. It is an invitation to keep asking, to keep refining our tools, and to keep listening to the subtle rhythms of the vacuum. It is an invitation to accept that clarity and mystery are not enemies, but partners that coexist in the heart of every great truth. There is a profound calm in that acceptance, a calm in knowing that understanding does not require final, absolute answers to be deeply meaningful. There is peace in recognizing that our curiosity does not have to resolve into a state of perfect certainty to be worthwhile. Gravity will continue to shape the architecture of the universe whether we have the final equations or not. The stars will continue to burn, the space between them will continue to expand, and the journey of human understanding will continue to move forward steadily, without any unnecessary hurry. As the night reaches its deepest point, we can see that the mismatch between our theories is actually a sign of the universe's richness. It suggests that there is always more to discover, another layer to peel back, and a deeper harmony to hear. We are like listeners to a great symphony who have understood the melody of the small and the rhythm of the large, but are still waiting for the final movement that brings them into a single, soaring chord. The weight is not a burden, it is part of the music. It keeps us attentive and keeps us searching. In the quiet space between what is known and what remains uncertain, discovery quietly lives and breathes. For now, it is enough to notice how much we have already learned, how much still invites our attention, and how gently the universe allows both the known and the unknown to exist at once. As you drift now into the final stages of rest, feel the steady and predictable pull of the earth beneath you. This is the same force that holds the atmosphere to our world, allowing you to breathe deeply and slowly. This is the same force that guides the moon through the night sky. Gravity is the ultimate anchor, a force of connection that binds you to the cosmos in a silent, unbreakable embrace. The tensions of the day and the complexities of the mind can now soften and fade, much like the flickering fluctuations of the quantum world settling into the smooth curves of space-time. You are supported by a reality that is far more stable and enduring than any temporary uncertainty. The universe is not rushing toward its conclusion, and neither are you. There is plenty of time for the answers to arrive, and there is plenty of room for the mysteries to remain. In this quiet openness, the journey of the whispering scientist comes to a gentle close for tonight. We have traveled from the grainy, restless heart of the atom to the sweeping geometric majesty of the stars. We have looked into the dark thresholds of black holes and listened for the fading echoes of the beginning of time. Through it all, we have found that the universe is a place of order, even where we cannot yet see the full design. We have found that patience is as much a part of science as mathematics itself. Now, let the weight of your body and the stillness of the air guide you into a state of total and restorative peace. The world is in good hands, governed by laws that are steady and patient. Gravity pulls downward, time moves forward, the questions remain, and the journey continues in the silence of your dreams. You are a part of the architecture, a part of the story, and a part of the mystery. Sleep now, knowing that the universe is whole, the story is far from over, and you are resting exactly where you are meant to be in the grand, patient design of the all.